There is a feeling you have known your entire life. It is a quiet, invisible, and constant presence. A simple, familiar pull that holds your feet to the ground, that keeps the oceans in their basins, and that guides the moon on its silent path across the night sky. It is gravity. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. But what if this gentle, predictable presence is also the greatest barrier to understanding our universe? What if, when you look closely enough, this everyday reality becomes a deep paradox, a puzzle that has remained unsolved for nearly a century? This is the story of why that simple feeling of being held to the earth is connected to the biggest unanswered question in all of physics. The clockwork world of Isaac Newton. For most of human history, gravity was simply a fact of life, as certain as the rising sun. Things fall. That is just how the world works. It took the mind of Isaac Newton in the 17th century to see it not just as an observation, but as a mathematical certainty. The story of the apple may be a legend, but the change it represents is very real. Newton's great insight was that the same force pulling the apple to the ground was also the force holding the moon in orbit around the Earth, and the Earth in orbit around the Sun. He gave us a simple and deeply powerful equation, the law of universal gravitation. It described the pull between two objects as being tied to their mass, and as something that faded gently with the square of the distance between them. Suddenly, the universe was no longer a realm of mysterious motions. It became a clockwork, a grand, intricate machine operating on predictable, universal laws. Newton's gravity allowed us to predict the orbits of planets with quiet accuracy, to understand the swing of a pendulum, and to feel the rhythm of the tides, which rise and fall as the moon's gravity tugs on our world's oceans. His work is so reliable that we still use its principles today to send probes into the far reaches of the solar system. This view of gravity is comforting. It presents a world that is smooth, continuous, and orderly. If you know the position and motion of every piece, you could, in theory, calculate the entire future and past of the cosmos. There are no sudden jumps, no fuzzy uncertainties. Gravity is a reliable presence. It always pulls, it never pushes, and its strength is perfectly known. For over 200 years, this picture of the universe was all we needed. It was so successful that some physicists at the end of the 19th century felt that the work of physics was nearly finished. But they could not have been more wrong. The clockwork universe was about to be undone, and the first quiet questions were already forming around gravity itself. Newton's law was perfect for describing how gravity worked, but it offered no explanation for why. How did the sun, 93 million miles away, reach across empty space and instantaneously tell the Earth how to move? Newton himself found this action at a distance to be an unsettling idea and left it as a puzzle for those who would come after. That puzzle would be solved by a man who would completely reshape our definition of reality. Einstein's vision and the fabric of spacetime. That man was Albert Einstein. In the early 20th century, Einstein was not trying to fix Newton's theory, but to reconcile it with his new theory of special relativity. If the speed of light was the absolute cosmic speed limit, then gravity's pull could not be instantaneous, as Newton's equation suggested. Einstein's decade-long intellectual journey led to his general theory of relativity in 1915, one of the most profound achievements of the human mind. His answer to the action at a distance problem was radical and beautiful. Gravity, he suggested, is not a force in the way we usually think of one. It is a consequence of the shape of spacetime itself. Imagine a flat, stretched rubber sheet. This is spacetime. Now, place a heavy bowling ball in the center. The ball creates a deep curve in the sheet. If you then roll a small marble nearby, it isn't pulled toward the bowling ball by a mysterious force. It simply follows the curve in the sheet that the ball's mass has created. The marble is traveling in the straightest possible line through a space that is no longer flat. This is what Einstein proposed is happening in the cosmos. As physicist John Archibald Wheeler later summarized, spacetime tells matter how to move, matter tells spacetime how to curve. The sun does not pull the Earth. It warps the fabric of spacetime around it, and the Earth follows that curvature, like a marble rolling around a gentle dimple. This was not just a beautiful idea. It made testable predictions that differed from Newton's theory in small but important ways. General relativity predicted that starlight should bend as it passes the massive sun, a prediction confirmed during a solar eclipse in 1919, making Einstein famous overnight. It correctly explained a tiny, persistent wobble in the orbit of Mercury that had long puzzled astronomers. Today, its effects are part of our lives. The GPS in your phone needs constant corrections because time actually moves slightly faster for satellites in orbit, where gravity is weaker, than it does for us on the ground. And in 2015, a century after his theory was published, scientists detected gravitational waves, ripples in the fabric of spacetime itself, created by the collision of two black holes more than 1 billion light-years away. It was a final, quiet confirmation of Einstein's vision. General relativity is our great theory of the large. It describes the universe on the grandest of scales, the dance of galaxies, the birth and death of stars, the deep mystery of black holes, and the expansion of the universe itself. It paints a picture of a smooth, continuous, geometric reality. And on its own terms, it is perfect. The problem is, it is only half of the story. The quantum world and the pixelated universe. While Einstein was reshaping our understanding of gravity, another group of physicists was starting a revolution on a completely different scale. The world of the very small. This was the birth of quantum mechanics, and it would reveal a reality stranger and more counterintuitive than anyone had imagined. Where general relativity is smooth and continuous, the quantum world is grainy and discrete. The word quantum itself refers to the discovery that energy and other properties at the subatomic level come in tiny, indivisible packets, or quanta. You cannot have half a quantum of light, just as you cannot stand on half a step of a staircase. Reality, at its most fundamental level, seems to be pixelated. Quantum mechanics tells us that particles like electrons do not have a definite position until they are measured. Instead, they exist in a superposition of all possible states at once, described by a wave of probability. A single particle can be in many places at the same time, and only when we look does it choose a location. It is a world of inherent uncertainty, a deep contrast to the deterministic clockwork of classical physics. Despite its strangeness, quantum theory is perhaps the most successful scientific theory in history. It is the foundation of our understanding of chemistry, materials science, and all of modern electronics. Without it, we would not have computers, lasers, or nuclear energy. From it, physicists developed what is now known as the Standard Model of particle physics. It describes 3 of the 4 fundamental forces of nature. The strong nuclear force, which holds atoms together, the weak nuclear force, which governs radioactive decay, and electromagnetism. In this picture, forces are carried by exchanging particles. For electromagnetism, the carrier is the photon, the particle of light. The Standard Model is a monumental achievement. It has been tested and verified in particle accelerators for decades. But there is a quiet, monumental omission. One force is left out entirely. The oldest, most familiar force of all, gravity. The 2 stories. Here, we arrive at the heart of the problem. We have 2 perfect descriptions of reality. General relativity, which beautifully describes the universe of the large, and quantum mechanics, which flawlessly describes the universe of the small. Both are incredibly successful in their own domains. But when you try to make them work together, they do not speak the same language. The mathematics falls apart, and the elegant equations that describe the universe return answers that are nonsense. The trouble begins when you try to describe gravity in the language of quantum mechanics. Following the pattern of the other forces, we would expect gravity to have a force-carrying particle, a quantum of the gravitational field. We even have a name for this imagined particle, the graviton. In theory, the pull you feel from the Earth is the result of exchanging countless gravitons with every atom in the planet. But when physicists tried to build a theory with gravitons, the math broke. The problem lies in what each theory describes. Quantum theories are built on a fixed, static stage, a flat spacetime background where particles interact. But in general relativity, spacetime is the stage, and it is not static. It is a dynamic player, constantly being bent and warped by the matter and energy within it. When you combine these ideas, you get an uncontrollable feedback loop. Particles, including gravitons, curve spacetime. But that curvature then changes how the particles travel, which creates new curvatures, and so on, in an infinite cascade. When you try to calculate the outcome of these interactions, especially at very high energies, the equations give you an infinite answer. A probability greater than 100%, which is simply mathematical noise. For most everyday situations, this disagreement does not matter. Gravity is incredibly weak compared to the other forces. The electromagnetic force between two protons is more than 42 orders of magnitude stronger than the gravitational force between them. On the scale of atoms, gravity is so faint it can be safely ignored. And on the scale of planets, quantum effects are so tiny they average out to nothing. But there are two places in the universe where this quiet peace is broken. The first is at the heart of a black hole. Here, an immense mass is crushed into a point of zero volume and infinite density, a singularity. To understand this point, you need general relativity for the extreme gravity and quantum mechanics for the microscopic scale. And our theories fail. The second place is the very beginning of the universe, the Big Bang. Our models suggest the entire observable universe was once compressed into a space far smaller than an atom. To understand our own origin, we need a theory that can handle both gravity and quantum effects at the same time. We need a theory of quantum gravity. Without it, the first moments of creation and the ultimate fate of a black hole remain quiet mysteries, locked behind a wall of infinity. The search for a solution, string theory. The search for a theory of quantum gravity is a modern-day quest. Einstein himself spent much of the last 3 decades of his life searching for a unified field theory that would describe all of nature's forces in a single framework. Since his time, 2 major ideas have emerged, each offering a radically different picture of the universe. The first and most famous is string theory. String theory proposes an elegant solution. It suggests that if you could zoom in on any particle, an electron, a photon, to an impossibly small scale, you would not find a point. You would find a tiny, one-dimensional, vibrating loop of energy. A string. The central idea is like that of a violin string. A single string can vibrate at different frequencies to produce different notes. In the same way, these fundamental strings can vibrate in different patterns. A string vibrating one way might appear to us as an electron. The same string vibrating another way would appear as a photon. And a string vibrating in yet another specific way would have the exact properties of the graviton, the quantum of gravity. In this picture, the entire diverse zoo of particles we see in the universe is nothing more than the different notes being played on a single kind of fundamental string. It is a vision of ultimate unity. This solves the problem of infinities because strings are not points. In the older theories, interactions happen at a single, zero-dimensional point, which causes the math to break. But strings are extended objects. Their interactions are smeared out. Instead of colliding at a sharp point, 2 strings merge and split smoothly, like the joining of 2 streams of water. This smearing is enough to wash away the infinities that arise at zero distance. The math, which previously returned nonsense, now yields finite, sensible answers. But this elegance comes with an unexpected requirement. For the mathematics to work, the theory requires that the universe has more dimensions than the 3 of space and 1 of time that we know. Most versions of the theory require 10 total spacetime dimensions, with some variations suggesting 11. Where are these extra dimensions? The proposed answer is that they are curled up, or compactified, to a size so small that we cannot perceive them. A common analogy is a garden hose. From a distance, it looks like a one-dimensional line. But as you get closer, you see it has a second, circular dimension. String theory suggests that at every point in our familiar space, there exists a tiny, complex, curled-up space of 6 or 7 extra dimensions. This leads to the biggest challenge for string theory. The theory does not seem to predict a single way for these dimensions to be curled up. Instead, it seems to allow for a staggering number of possibilities, perhaps 10 to the power of 500 or more, each corresponding to a universe with its own unique physical laws. With so many possible universes, how can we use it to explain why our universe is the way it is? Furthermore, the strings themselves are thought to exist at an energy scale quadrillions of times higher than what our most powerful particle accelerators can achieve. This makes testing the theory directly an almost impossible task, leaving it, for now, as a beautiful and mathematically consistent idea with no clear connection to the world we can measure. The search for a solution. Loop quantum gravity. While string theory has often been in the spotlight, a second, powerful idea has been developed in parallel. It takes a completely different approach. This is loop quantum gravity, or LQG. If string theory's starting point is to quantize stuff by replacing particles with strings, loop quantum gravity's starting point is to take Einstein's theory of gravity and quantize space and time itself. It does not require extra dimensions or new particles. Instead, it makes a bold and profound claim. The fabric of spacetime is not a smooth sheet. It is a network, woven from a finite number of discrete, quantum loops. Imagine a t-shirt. From a distance, it looks like a smooth, continuous cloth. But under a microscope, you see it is woven from individual threads. Loop quantum gravity suggests that spacetime is like this. What we perceive as smooth space is, at the smallest scale, a granular structure, a shimmering network of interconnected loops of gravitational field. These loops are not in space, they are space. You cannot have a distance smaller than the size of one of these loops. There are atoms of space and time. This pixelation of reality has a profound consequence. It automatically cures the problem of infinities. In a world where there is a minimum possible size, you can no longer have a singularity, a point of zero volume. An infinite density becomes impossible. This leads to a radically new picture of black holes and the Big Bang. In the world of loop quantum gravity, a collapsing star does not form an infinitely dense singularity. Instead, matter is compressed until it can be compressed no further, until it reaches the fundamental graininess of spacetime. At this point, the immense gravitational pull would theoretically reverse into an equally immense outward push. This is called a big bounce. This idea completely reframes our cosmic history. The Big Bang may not have been the beginning, but rather a bounce from a previous, collapsing universe. A black hole might not be an eternal prison, but a gateway. Matter falling in would be crushed to an extreme state and then bounce, perhaps re-emerging somewhere else in spacetime, or even forming the seed of a new universe. Loop quantum gravity is a compelling alternative. It arises directly from applying quantum rules to Einstein's theory without extra ingredients. However, it faces its own challenges. One of its greatest struggles has been to show how the smooth, classical spacetime of Einstein's theory emerges from this underlying quantum foam. And, like string theory, it suffers from a lack of experimental evidence. The predictions it makes are at the very edge of our current technological capabilities, and so far, none have been confirmed. The quiet and the way forward. String theory and loop quantum gravity are the two leading ideas, but they are not the only ones. There are other fascinating paths of research, each looking at the problem from a different angle. But all of them, for all their mathematical beauty, run into the same quiet place: the experimental desert. The energy required to directly probe the scale where quantum gravity effects should become obvious is about 100 trillion times greater than the energy of our most powerful particle accelerators. Building a machine to reach these energies would, with current technology, require something larger than our galaxy. This is what makes quantum gravity the biggest unsolved problem. It is not just that we do not have the right theory, it is that we have very few experimental clues to guide us. Physicists are left to move forward guided primarily by principles of mathematical consistency and elegance. This is a unique situation in the history of science. From Newton to Einstein to the quantum pioneers, theory and experiment have always walked hand in hand. Experiments would reveal new phenomena, and theorists would work to explain them. Theorists would make new predictions, and experimentalists would race to test them. In the quest for quantum gravity, this vital dialogue has fallen silent. So, where do we go from here? Physicists are pursuing more subtle, indirect tests. Astronomers are studying data from gravitational wave detectors, hoping to find tiny deviations from general relativity near black holes. Cosmologists are searching for faint, primordial signatures in the cosmic microwave background that might favor one theory over another. They are listening for a faint whisper from the very beginning of the universe, hoping it tells a story we can finally understand. The enduring mystery. We began with the simple, everyday pull of the Earth beneath our feet. We journeyed from Newton's clockwork world to Einstein's curved spacetime, and into the strange, probabilistic realm of the quantum. And we have ended here, at the edge of human knowledge, looking across a quiet chasm that separates our two best descriptions of reality. The conflict between the smooth world of general relativity and the pixelated world of quantum mechanics is more than a mathematical problem. It is a deep crack in the foundations of our understanding. To solve it is to answer the most fundamental questions we can ask. What is spacetime made of? What happens at the center of a black hole? What, if anything, came before the Big Bang? The quest for quantum gravity has pushed the boundaries of mathematics and imagination, forcing us to reconsider the nature of space, time, and reality itself. The final theory may look like one of the ideas we have now, or it may be something else so strange and profound that we have not even dreamed of it yet. The familiar pull you feel right now, the force that tethers you to this world, is a constant, gentle reminder of the greatest gap in our knowledge. It is a whispered secret from the cosmos, a challenge posed to us by the universe itself. And the quest to unravel that secret, to understand that final piece of the cosmic story, is the most profound journey we have ever embarked upon. Einstein's rubber sheet analogy that accidentally broke physics. There is an image of gravity so familiar it has become part of our shared understanding of the universe. It's Einstein's idea of a rubber sheet, where large objects tell the fabric of the universe how to bend. We've all seen some version of it. A heavy ball placed on a trampoline, creating a gentle well. A smaller marble, rolled nearby, follows that curve, spiraling toward the center. It is a simple and elegant picture, one that gives a quiet, aha, moment. But sometimes, the simplest pictures, the ones we see most often, are the ones that hide the most interesting questions. This simple analogy holds within it a subtle confusion, a series of quiet omissions that, once seen, help us understand why our modern picture of the universe is still incomplete. We are going to look closely at this image, and in doing so, we will find ourselves looking into one of the deepest unsolved mysteries in science. The beautiful picture, building the analogy. Before we explore its limits, we have to appreciate how revolutionary this picture is. For more than 200 years, the world understood gravity through the mind of Isaac Newton. His vision was of a mysterious and invisible force. An apple falls, the moon orbits the Earth, all because of an unseen pull that acts instantly across empty space. Newton himself was troubled by this. How could two objects, separated by millions of miles, influence each other across a vacuum? He wrote that the idea of one body acting on another without any mediation is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. He knew it was a gap in his theory, but the mathematics worked so well that the question was quietly set aside. For 2 centuries, gravity was simply a force, an unexplained action at a distance. Then, in 1915, a clerk in a Swiss patent office offered a new reality. Albert Einstein proposed that space is not just an empty stage. Instead, he said that space and time are woven together into a single, 4-dimensional fabric, spacetime. And this fabric is not rigid, it can be bent and warped by the presence of mass and energy. This is the heart of general relativity, and it is where our rubber sheet analogy is born. Imagine that flat sheet again. In a universe with no matter, it is perfectly level. An object would travel across it in a straight line, forever. But if we place a heavy ball, our sun, in the middle, the sheet sags, creating a curved dip. This, Einstein said, is what the sun does to the 4-dimensional fabric of spacetime. Now, if we roll a small marble, our Earth, nearby, it doesn't get pulled by an invisible strain. It simply follows the curve of the sheet. It is trying to move in the straightest line possible, but the straightest line on a curved surface is a curve. Physicists call this path a geodesic. And that geodesic is what we see as an orbit. The Earth is not being pulled. It is following the straightest available path through a spacetime that has been curved by the sun. The physicist John Wheeler famously summarized it this way. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. It is a beautiful, reciprocal relationship. This was more than just a nice idea. It made predictions that could be tested. It explained a small wobble in Mercury's orbit that Newton's laws could not. It predicted that even massless light should bend when passing a massive object, because it too must follow the curves of spacetime. This was confirmed during a solar eclipse in 1919, when starlight was seen bending around the sun, just as Einstein had calculated. The rubber sheet analogy became the public face of this new understanding. It took an incredibly abstract, mathematical idea and made it feel intuitive. It shows gravity not as a force, but as geometry. For a general understanding, it's a brilliant piece of communication. And yet, it contains a few subtle but fundamental misdirections, a series of flaws that point toward the quiet conflict at the very heart of modern physics. The first crack, the problem of self-reference. This is where we begin to look a little closer. Let's return to the analogy. A bowling ball on a rubber sheet. Why does the ball make a dip? The ball sinks because the Earth's gravity is pulling it down. The entire demonstration relies on the very thing it is trying to explain, gravity. It's a circular argument. You are using gravity, the Earth pulling the ball, to make a model of gravity, the marble rolling into the dip. This might seem like a small simplification, but it plants a misleading idea in our minds. It suggests that for spacetime to curve, it must bend into some other, higher dimension, just as the 2D sheet bends into our 3D space. But that is not how general relativity works. Spacetime does not need another dimension to curve into. The curvature is intrinsic, a property of the fabric itself. Imagine an ant living on the surface of a large balloon. To the ant, its world is 2-dimensional. It knows only forward, backward, left, and right. It has no concept of up or down, away from the surface. If 2 ants start at the balloon's equator and walk straight toward the North Pole, they will find themselves getting closer together, eventually meeting at the pole. To them, it might seem as if a mysterious force is pulling them together. But from our three-dimensional view, we can see there is no force. They are simply following straight lines on a curved surface. The curvature is a property of the balloon itself. The rubber sheet analogy misses this quiet but crucial point. By using gravity to explain gravity, it trades a deep truth for a simple visual. The geometry of the universe is not being pulled from the outside, it is being shaped from within. This is the first important way the analogy can be misleading, but the next is even deeper. The missing dimension. Where is the time in spacetime? Einstein's great insight was not just that space is curved, but that spacetime is curved. Our rubber sheet analogy does a good job of showing a 2D surface being distorted, representing curved space. But a key part of the story is missing: time. By leaving out time, the analogy overlooks the most profound consequence of gravity. In general relativity, gravity doesn't just warp space, it warps time. In fact, for things like the Earth's orbit, the warping of time is a much larger effect than the warping of space. Clocks closer to a massive object run slower than clocks farther away. This is called gravitational time dilation. This is not a theoretical idea. It is a measured fact that affects our daily lives. The GPS in your phone relies on satellites, each with a very precise atomic clock. These clocks are affected by two relativistic effects. Because they are moving fast, their clocks slow down by about 7 microseconds per day. But because they are farther from Earth's gravity, their clocks speed up by about 45 microseconds per day. The net result is that GPS satellite clocks run faster than clocks on the ground by about 38 microseconds every day. It sounds like a tiny amount, but if engineers did not correct for this, GPS navigation would fail. Positional errors would grow by about 10 kilometers every single day. So, gravity slows down time. The stronger the gravity, the slower time flows. How does the rubber sheet represent this? It doesn't. The marble moves through curved space, but the real insight of relativity is that all objects are always moving through spacetime. When spacetime is curved, it is not just spatial paths that are altered, the path through time is also changed. An orbiting planet is following a geodesic, the straightest possible path, through four-dimensional spacetime. It follows the curve in space because that is the path that allows it to travel most efficiently through the combined fabric of space and time. The rubber sheet, by showing only a static curve in space, misses this dynamic, temporal element. It suggests gravity is about bent space, but in our solar system, it is mostly about warped time. And this omission leads to a third, subtle flaw in the model. The straightest path, the illusion of force. There is one more piece of misdirection in the rubber sheet analogy. When we watch the marble roll down the slope made by the bowling ball, our minds see acceleration, a force. It looks like the marble is being pulled, just as Newton described. The slope seems to provide the force that makes it move. But this is the very illusion general relativity was meant to move past. In Einstein's universe, gravity is not a force. An object in free fall feels no force at all. An astronaut floating in the International Space Station is in a constant state of free fall around the Earth, and they are weightless. From their perspective, they are not accelerating, they are simply coasting. According to Einstein, that astronaut is moving in a straight line. A geodesic is the spacetime equivalent of a straight line. The Earth, the Moon, and the astronaut are all just following the straightest possible paths through a curved universe. The appearance of a bent orbit is a result of the curved stage, not a force pushing the actors around. The rubber sheet analogy betrays this idea. The rolling marble is acted on by forces, including the friction that causes it to lose energy and spiral inward. That is why the marble in a demonstration never has a stable orbit, it always spirals to the bottom. Planets, however, can maintain stable orbits for billions of years because there is no friction and no down for them to be pulled into. The analogy accidentally reintroduces the very idea of a gravitational pull that Einstein's geometry was meant to replace. So, we have a picture that is beautiful but incomplete. It uses gravity to explain gravity. It shows us curved space but leaves out warped time. And it makes us see a force where there is only geometry. Each of these is a quiet misdirection. But together, they point to something much larger. The place where our understanding of physics itself becomes incomplete. The shredded fabric, the quantum breakdown. For more than a century, our understanding of the universe has been guided by two great theories. General relativity is Einstein's theory of the very large, describing the graceful, geometric dance of stars and galaxies. The other is quantum mechanics, the theory of the very small, which describes the strange, probabilistic world of atoms and particles. Both theories have been incredibly successful in their own domains. The problem is, they are fundamentally incompatible. Relativity assumes a smooth, continuous spacetime. Quantum mechanics suggests that at the smallest scales, reality may be pixelated, grainy, and uncertain. This is where the rubber sheet analogy offers its final, accidental insight. It gives us a picture of a perfect, unbroken sheet. But what happens if we zoom in on this fabric, all the way down to the smallest possible scale, a length known as the Planck length? At this impossibly small scale, the smooth fabric of spacetime that Einstein imagined is thought to dissolve into something else entirely. The principles of quantum mechanics suggest that spacetime itself should be filled with tiny, fleeting fluctuations of energy. Virtual particles pop in and out of existence, creating miniature curvatures and bubbles of spacetime. The physicist John Wheeler called this idea quantum foam. At this scale, spacetime may no longer be a smooth sheet. It could be a shifting, probabilistic foam. The very idea of a precise location or a smooth path would break down. When we try to apply Einstein's equations, which are built on smooth geometry, to this chaotic, uncertain world, the math gives us nonsensical answers, like infinities. This is the heart of the conflict. General relativity is like an analog theory for a continuous world. Quantum mechanics is like a digital theory for a discrete world. The rubber sheet analogy is a classical picture, and its smoothness is an illusion. The real fabric of the universe, we suspect, is a quantum tapestry. The analogy is incomplete in the same way, and for the same reason, that general relativity itself becomes incomplete. It cannot account for the quantum nature of reality. The unsolved mystery, where physics is incomplete. This quiet conflict between our theory of the large and our theory of the small is not just a philosophical puzzle. It is a wall that stands between us and an understanding of the most extreme places in the universe. There are two places where gravity is incredibly strong and happens in an incredibly small space, where both general relativity and quantum mechanics must apply at the same time. The first is the center of a black hole. General relativity predicts a singularity, a point of infinite density where the curvature of spacetime becomes infinite. But infinity is often a sign that a theory has reached its limits. We need a theory of quantum gravity to understand what truly happens to matter and spacetime there. We don't know, because our two best theories give us different stories. The second is the origin of our universe, the Big Bang. Our models suggest the entire observable universe was once compressed into a space smaller than an atom. To understand these first moments, we need a theory that can describe the quantum behavior of gravity. What was the state of the universe at the very beginning? Was there a before? These are some of the biggest questions we can ask, and the answers are hidden behind a door that only a theory of quantum gravity can open. The incompleteness of physics is this fundamental divide. We have two sets of rules for reality, and we do not yet know how to reconcile them. Scientists are exploring many paths, from string theory to loop quantum gravity, but for now, the final picture remains out of reach. We began with a simple, intuitive picture: a heavy ball on a trampoline. We admired its elegance and its power to explain the orbits of planets. But then, we looked closer. We saw how it used gravity to explain gravity, how it left out the dimension of time, and how it quietly suggested a force where there is only geometry. We saw that the smooth, simple sheet was an incomplete picture. And in seeing those limits, we saw something important. The analogy's limitations are a metaphor for the limits of general relativity itself. The smooth, classical world gives way to a jittery, quantum one. The beautiful sheet, when we look close enough, begins to fray. Einstein's analogy did not break physics. Physics was already in two parts, two beautiful stories that did not yet fit together. What the analogy accidentally did was give us a perfect, tangible way to see *y. It shows us the dividing line. On one side, the graceful, sweeping curves of the cosmos. On the other, the strange, uncertain world of the quantum. And we are living in the space between them, still searching for the bridge that will finally make our picture of the universe whole. If this kind of quiet exploration into the world of physics helps you unwind, consider liking the video and subscribing to the channel. And a question to leave with you: if gravity is not a pull, but the shape of the world you are moving through, does that change the feeling of the ground beneath your feet? Feel free to share your thoughts in the comments. Schrödinger's cat explains slowly for sleep. Our universe appears to play by two different sets of rules. For most of human history, we knew only one: a world of comforting certainty, of apples falling from trees and planets tracing predictable, elegant paths. It was a clockwork universe, solid and real. But at the turn of the 20th century, scientists began to explore a new realm, a world of atoms and particles, and what they found there was deeply, profoundly strange. The solid ground of our reality dissolved into a fog of probability. This is a journey to the border between those two worlds. It is not a puzzle to be solved, but a landscape to be wandered. It is a quiet story about a cat, a box, and a single, flickering atom. A story that asks a profound question: is something real only when we are looking at it? Settle in, and let's journey together into the heart of that mystery. Let the world outside this story disappear. There is only the darkness, the quiet, and the gentle unfolding of an idea. Before our story can begin, we must set the stage. Imagine a room, silent and empty. In its center sits a box made of steel, sealed completely against all light, all sound, all influence from the world outside. It is an island of isolation, a tiny, private universe. Inside this silent, dark universe, we place our first character, a cat. This cat is a creature of our world, the classical world. It is a living, breathing thing, its existence solid, real, and undeniable. A cat is either here or there, asleep or awake, living or not. It obeys the physics of our everyday experience. Now, we introduce the other characters in our quiet play. Next to the cat, we place a delicate and macabre device. First, a tiny piece of radioactive material. We are interested in just one of its atoms, a single, solitary, unstable atom. This atom is the heart of our story. It lives on a knife's edge of existence. In the next hour, there is a 50-50 chance it will decay, and an equal chance it will not. It is perfectly balanced between two futures, like a coin tossed high in the air, spinning and spinning, not yet heads and not yet tails. It hangs in a state of pure potential. Connected to this atom is a detector, a Geiger counter. Its job is simple: to listen for the click of that single atom decaying. If it detects the decay, it will trigger the next part of the machine, a small hammer, held by a delicate latch. When the signal comes, the latch will release, and the hammer will fall. The hammer will strike a fragile vial of deadly poison. If the vial shatters, the cat's story ends. If the atom does not decay, the detector remains silent, the hammer remains held, and the cat continues to sleep peacefully. All these elements are now sealed inside the box. The stage is set. The clock begins to tick. And inside that steel chamber, a question begins to form that would shake the foundations of physics. To understand the strangeness about to unfold, we must understand that our universe has two faces. There is the classical world of Isaac Newton, a world where everything has a definite place and a definite speed. If you know the starting conditions, you can calculate the future with perfect certainty. For centuries, we believed these rules governed everything, from a grain of sand to the most distant star. It was a reassuring thought, a world with no fundamental ambiguity. But as scientists looked deeper, into the realm of atoms and the particles that build them, the familiar, clockwork rules seemed to melt away. This new world was the quantum world, and its rules were unlike anything ever encountered. Down at this microscopic level, a particle like an electron doesn't have a single, definite location until you measure it. Instead, it exists as a wave of probability, a cloud of possibility. It is, in a way, everywhere it could possibly be, all at once. It is only when an observation is made, when you look, that this cloud of potential suddenly collapses into a single, definite point. Before the observation, the particle exists in a state physicists call superposition, a blending of all its possible states, coexisting simultaneously. This discovery was revolutionary and deeply unsettling. It shattered the dream of a perfectly predictable universe. Albert Einstein famously disliked it, declaring, "God does not play dice." He believed there had to be a deeper reality we just weren't seeing yet. But experiment after experiment confirmed the bizarre nature of the quantum realm. And it is these strange, dreamlike rules that govern the single atom inside our box, the atom that holds the cat's fate in its uncertain hands. This is where the solid, classical world of the cat and the misty, quantum world of the atom are about to collide. The most famous demonstration of this quantum weirdness is the double-slit experiment. Imagine a wall with two thin slits, a device that fires electrons one by one, and a screen on the other side. If we cover one slit, the electrons form a single band on the screen. This makes sense. It's like throwing tennis balls through a hole in a fence. The strange part happens when we open both slits. Common sense would tell us we should see two distinct bands, one behind each slit. The electrons, being tiny particles, should go through either the left or the right. But that is not what happens. Instead, a complex pattern of many light and dark stripes appears. It is an interference pattern, the kind you see when waves in a pond overlap. But we are firing electrons one at a time. The only way this is possible is if the single electron, as a wave of probability, does not choose a path. It goes through both slits at the same time. Its own wave of potential interferes with itself, creating the pattern. It is only when it strikes the screen, the moment of measurement, that the wave collapses, and the electron appears as a single particle in a single spot. Even stranger, if you place a detector at the slits to see which path the electron really takes, the interference pattern vanishes. The act of looking forces the electron to behave like a simple particle again. It's as if the universe refuses to show you its secret. This wave of potential is what physicists call the wave function. For our radioactive atom, its wave function describes its two possible states, decayed and not decayed. According to quantum mechanics, as long as the atom is unobserved, it is not one or the other. It is both. It is in a perfect superposition. And it is this shimmering, uncertain state of the atom that now begins to infect everything else in the box. Let us return to the silence of our steel box. An hour has passed. In our world, the classical world, the answer is simple. The atom either decayed or it did not. The cat is either alive or dead. Opening the box is simply an act of discovery. But the rules of the quantum world suggest something far more profound. Inside the box, the atom's fate is not yet decided. It exists as a perfect 50-50 blend of decayed and not decayed. It is in a superposition. But the fate of the atom is inextricably linked to the rest of the system. If the atom is in a superposition, then the Geiger counter must also be in a state of triggered and not triggered. And the hammer? It, too, is drawn into this quantum dream, in a superposition of fallen and not fallen. And the poison? It is released and contained. You can see where this is going. Each part of the chain has been pulled from our solid, classical world into the misty, probabilistic realm of the quantum. The boundary has been blurred. And so, we arrive at the cat. Its fate is tied to the poison. If the entire system exists in a state of superposition, then the cat, too, must be in a superposition. According to this strange logic, the cat is literally both alive and dead at the same time. This is the central, shocking conclusion of the thought experiment. The quantum uncertainty of a single atom has leaked out and infected a large, macroscopic object, forcing it into a state that defies all common sense. The wave function of the entire box now describes a universe where a cat is alive and a universe where a cat is dead, both folded together. For as long as the box remains sealed, this bizarre, dual reality persists. The question, is the cat alive or dead, is a meaningless question, like asking a spinning coin, are you heads or tails? The cat's reality is a haze of potential, a dream from which it has not yet woken. This dream, however, cannot last forever. The story is not over until the box is opened. The act of observation, in quantum mechanics, is the mysterious bridge between the world of potential and the world of actuality. It is the moment we call the collapse of the wave function. Imagine reaching out to open the lid. The moment information from inside can escape and reach our eyes, the universe is forced to make a choice. The delicate superposition cannot survive contact with the outside world. The wave function, holding two possibilities, instantly collapses into one single, definite reality. The cloud of probability condenses into a single droplet of fact. The atom becomes either decayed or not decayed. And the cat is either definitively, unambiguously alive, purring as the light hits its eyes, or it is definitively, unambiguously dead. We will never open the box to find a half-alive, half-dead ghost cat. We will only ever find one of two outcomes. The quantum magic happens only when no one is looking. This is the measurement problem, one of the deepest mysteries in all of science. What is it about measurement that is so special? Does it require a conscious observer? Or is any large-scale interaction enough? The debate continues to this day. But the central point of the story remains. There is a sudden leap from a state of many possibilities to a state of one single reality. A moment of waking from the quantum dream. It is easy to hear this story and believe that physicists were seriously proposing the existence of zombie cats. But that was not the point at all. In fact, it was the exact opposite. The physicist Erwin Schrödinger devised this thought experiment in 1935 not to champion quantum weirdness, but to argue against it. He found the prevailing interpretation of the time to be absurd. He created the story of the cat to say, look at the nonsense your theory leads to. If your rules are correct, then a cat can be both alive and dead. Since this is obviously not true, there must be something wrong with your interpretation. He was using the cat to magnify the quantum strangeness to a scale where it becomes undeniably paradoxical. His question was profound. Where do the quantum rules stop and the classical rules begin? Why does an electron get to exist as a wave of potential, but a cat, which is just a collection of particles, does not? Today, most physicists have a more refined answer. It revolves around an idea called quantum decoherence. This theory suggests that a quantum superposition is incredibly fragile and can only be maintained in near-perfect isolation. The moment a quantum system interacts with its environment, even by bumping into a single air molecule, its wave function becomes entangled with the countless particles of that environment. This vast interaction effectively washes away the delicate superposition, forcing the system to decohere into a single, classical state almost instantly. A cat is an enormous, complex, warm system. It is constantly interacting with its environment, breathing air and radiating heat. These countless interactions would destroy any potential superposition so rapidly that, for all practical purposes, it could never form. The cat, through its own complexity, is constantly measuring itself, forcing itself to be either alive or dead. The paradox is resolved because the conditions for it, perfect isolation for a macroscopic object, can never truly be met. The story was a brilliant fiction designed to reveal a deep truth about the border between two worlds. The story of Schrödinger's cat is not really about a cat. It is about our relationship with reality. It reminds us that the world, when we look away, might be a far stranger and more fluid place than we can possibly imagine. The universe, at its most fundamental level, is not a collection of tiny, solid things, but a shimmering ocean of potential. And we, the observers, by the simple act of looking, participate in collapsing those waves into the solid shore of the world we know. If you enjoyed drifting through these quiet explorations of science, consider subscribing and joining us for more journeys into the beautiful mysteries of our universe. For now, though, it is time to let this story fade. Let the image of the box, the atom, and the cat dissolve back into the quiet darkness. The questions will remain, hanging in the air like dust motes in a sunbeam. Some stories are not meant to give answers, but to deepen our sense of wonder. The world is filled with a quiet magic, hidden just beneath the surface of things. A world of spinning coins and waves of possibility. Let your mind drift on that thought. The deep, strange, and beautiful connection between the smallest of things and the largest of ideas. Let the wonder carry you now, into a peaceful, quiet sleep. Fade into the quiet, fade into the dark, rest now. The equation that proves modern physics is wrong. For much of the last century, our understanding of the universe has been guided by two remarkable stories. Each one describes a different part of reality, and each one does so with an accuracy that is difficult to overstate. One story is that of general relativity, our narrative for the cosmos, for the silent turning of planets, the lives of stars, and the graceful arrangement of galaxies. The other is the standard model of particle physics, our guide to the world of the infinitesimally small, a place of strange and restless quantum particles. In their own realms, they are two of the most successful ideas ever imagined. But there is a quiet tension hidden within them. For decades, the deepest hope in physics has been to unite these two stories into a single, seamless description of reality, a theory of everything. It would be a set of rules that could explain the universe from its first moment to its last. Yet when we try to write this unified story, when we gently combine the mathematics of the very large with the mathematics of the very small, something goes wrong. The equation doesn't just fail. It gives an answer that makes no physical sense: infinity. This isn't a small error or a minor puzzle. It is a profound and quiet message from the universe itself, a sign that our two most celebrated descriptions of the world are, in some deep way, incomplete. And this single, impossible number is the clue that tells us our story of reality is not yet finished. The two towers of knowledge. To understand this quiet conflict, we first have to appreciate the quiet triumph of what we are trying to connect. We have to stand in the shadow of these two towers of modern physics and feel a sense of wonder at their power. The first tower is Albert Einstein's vision, the theory of general relativity. Before Einstein, we thought of gravity as a force, an invisible cord pulling things toward each other. Einstein proposed something different, and far more elegant. He suggested that gravity is not a force at all. It is the consequence of mass and energy gently warping the fabric of reality itself. He imagined that space and time are not a fixed background, but a single, dynamic entity, spacetime. The familiar analogy is of a heavy ball resting on a stretched sheet. The ball creates a gentle curve in the fabric. A smaller marble rolled nearby will follow this curve, circling the larger ball not because of a mysterious pull, but because it is simply traveling along the shape of the surface. This is what gravity is. The physicist John Wheeler described it with a simple poetry. Spacetime tells matter how to move. Matter tells spacetime how to curve. This idea led to predictions that changed how we see the universe. Einstein's equations suggested that the light from distant stars should bend as it passes the sun, a prediction confirmed during a solar eclipse in 1919. His theory explained a small, persistent difference in the orbit of Mercury that had puzzled astronomers for centuries. And 100 years later, it predicted that the collision of two black holes should send out ripples in spacetime itself. In 2015, the LIGO experiment detected these gravitational waves from 1 billion light-years away, a signal so faint it moved its detectors by less than the width of a single proton. General relativity works. It describes the world of the large, planets, stars, and the expansion of the universe, with a quiet and flawless precision. It is a classical story, a world of smooth curves and predictable paths. But what happens when you leave this majestic, slow-moving world and zoom in? Far past the planets and the atoms, into the realm of the subatomic. Here, the elegant, predictable curves of Einstein's universe give way to a reality that is chaotic, uncertain, and deeply strange. This is the world of our second tower, quantum mechanics. If general relativity is a slow and stately dance, quantum mechanics is a frenetic, flickering light. In this realm, particles are not like tiny, solid spheres. They are more like clouds of possibility. An electron doesn't have a single, definite location until it is observed. Until then, it exists in a superposition, a smear of all the places it could be at once. The rules here are not of clear cause and effect, but of probability and chance. It is a world built from discrete, indivisible pieces, or quanta. The story of this world is told by the Standard Model of particle physics. It is, perhaps, the most successful scientific theory in human history. The Standard Model describes every fundamental particle ever discovered. It lays out the cast of characters, the quarks that form protons and neutrons, the leptons like the electron, and the ghostly neutrinos that pass through us by the trillion every second. And it describes 3 of the 4 fundamental forces that govern how they interact: the electromagnetic force, the weak nuclear force, and the strong nuclear force. The predictive power of the Standard Model is almost beyond comprehension. For example, its prediction for a subtle magnetic property of the electron matches experimental measurements to an accuracy of better than 1 part in a billion. That is like measuring the distance from New York to Los Angeles and being correct to within the width of a human hair. It predicted the existence of particles like the W and Z bosons, the gluon, and the Higgs boson, decades before we had the technology to find them. So, we have these 2 monumental stories. One for the very large, one for the very small. One classical and smooth, the other quantum and granular. Both are astonishingly successful. And for most of modern science, having 2 separate stories has been enough. An astrophysicist studying a distant star can use general relativity and safely ignore the quantum world. A particle physicist at the Large Hadron Collider can use the Standard Model and mostly ignore gravity, because at the scale of particles, it is almost unthinkably weak. But if you look closely at the Standard Model's list of forces, you may notice something is missing. The one force we feel every moment of our lives. Gravity. It is simply not there. Not because it was forgotten, but because every time physicists have tried to include it, the 2 stories no longer align. Where the 2 stories meet. For a physicist, having two separate rulebooks for the universe is not just untidy. It is a sign that we are missing a deeper, more complete picture. The ultimate dream is to find a way to unite them, to weave general relativity and quantum mechanics into a single, quiet narrative. A theory of everything. This is not just a desire for neatness. It is a necessity. There are places in the universe where the two realms must overlap. Think of the very center of a black hole. General relativity calls this a singularity, a point where an immense mass is crushed into a space with zero volume, a place of infinite density. Here, you have the ultimate gravitational field, the domain of general relativity, but confined to an infinitesimally small point, the domain of quantum mechanics. To describe what truly happens there, you would need both theories at the same time. The same is true for the first moments of the Big Bang, when the entire universe was smaller than an atom. To understand our own origins, we need a theory of quantum gravity. But when we try to build that theory, we find that the two stories are written in fundamentally different languages. General relativity speaks the language of geometry, describing a universe that is smooth and continuous. Think of it like a ramp. You can stand at any point along its surface. Quantum mechanics, however, speaks the language of discrete mathematics and probability. Its world is quantized, coming in indivisible pieces. Its reality is more like a staircase. You can be on one step or the next, but never in between. Trying to write a single equation using both sets of rules is like trying to write a sentence that obeys the grammar of two different languages at once. The result is often confusion. You can even see this tension in Einstein's own field equation. The left side of the equation describes the smooth geometry of spacetime, while the right side describes the matter and energy that create the curvature. But all of that matter and energy is, at its core, quantum. It is granular, probabilistic, and strange. The equation connects a classical world with a quantum one. This is where the problem of infinity appears. When physicists try to force the two together using the standard methods of quantum field theory, the calculations break down. As they try to calculate interactions at higher and higher energies, corresponding to smaller and smaller distances, the mathematics begins to unravel. The equations start to predict that certain probabilities are not a finite number, but are instead infinite. An infinity is not a number that can describe a physical quantity. When it appears in an equation, it isn't the answer. It is a signal that the theory has reached its limit and no longer makes sense. It is the universe quietly telling you that your story is incomplete. Now, some of you may think this problem sounds familiar. And you would be right. When quantum theory was first developed, similar infinities appeared. For a time, it seemed like a serious flaw. But then, physicists developed a clever mathematical technique called renormalization. In simple terms, renormalization is a way of organizing the infinities. Physicists realized they could be absorbed into a few quantities that we can measure in experiments, like the mass and charge of an electron. You take the theoretical, bare, value, add the infinite correction term that arises in the math, and set the total equal to the finite value you actually measure in a lab. It seemed a little like hiding a mess instead of cleaning it up, but it worked remarkably well, leading to the incredible predictions of the Standard Model. So, why can't we just do the same thing for gravity? The problem is that gravity is different. For the other forces, the infinities were manageable. But the infinities that appear with gravity are more persistent. While the technical reason is complex, the core idea is that unlike other forces, gravity's interaction becomes more and more significant at higher energies. This creates not just a few infinities that can be neatly tucked away, but an infinite number of them. The method of renormalization no longer works. In the language of physics, gravity is perturbatively non-renormalizable. This is not just an opinion, it's a mathematical fact. The standard methods that gave us our most successful theory of the small are mathematically shown to fail when applied to gravity. The conflict is real, and the infinity it produces is like a quiet crack in the foundation of modern physics. The search for a deeper story. If the standard path leads to a dead end, perhaps we need a new path altogether. For the past 50 years, the most well-known, ambitious, and widely discussed candidate for this new idea has been string theory. String theory offers a proposal that is both simple and profound. It suggests that if you could look at any fundamental particle, an electron, a photon, a quark, at an impossibly small scale, you would find it is not a point at all. You would find a tiny, one-dimensional, vibrating filament of energy. A string. That is the entire foundation. In this view, the universe is like a cosmic symphony. Just as a violin string can produce different musical notes by vibrating in different patterns, a single fundamental string can appear as different particles. A string vibrating in one way acts like an electron. Vibrate it another way, and it becomes a photon. All matter and all forces are just different notes played by these tiny strings. The quiet beauty of this idea is that it promised to heal the divide in physics. Crucially, one of the predicted vibrational patterns of the string has the exact properties of the graviton, the hypothetical quantum particle of gravity. String theory doesn't need to force gravity into the picture. It emerges naturally from the theory itself. It is simply part of the symphony. Even better, string theory seemed to soothe the problem of infinities. The infinities in the older theories arose because particles were treated as dimensionless points. When two points get infinitely close, their interaction can become infinite. But strings are not points, they have a tiny, but real, length. This small bit of extension smooths out the interactions. By replacing points with strings, the theory seemed to tame the infinities that had troubled physics for so long. For a time, it felt like a solution was near. But as the decades passed, the elegant initial picture became far more complex. The first and most famous challenge is the problem of extra dimensions. For the mathematics of string theory to be consistent, it requires the universe to have more than the 3 dimensions of space and 1 of time that we experience. In some versions, as many as 10 or 11 spacetime dimensions in total. So, where are they? The proposed answer is that the extra dimensions are compactified, curled up on themselves at an unimaginably small scale, so tiny we cannot see or access them. Imagine looking at a garden hose from far away. It appears as a one-dimensional line. But up close, you see it has a second, circular dimension. The extra dimensions of string theory are thought to be like that, only trillions of times smaller. It's a clever idea, but it remains an idea without any experimental evidence. A second, deeper problem emerged. It turns out there isn't just one version of string theory. The equations allow for a vast number of ways to curl up those extra dimensions. Each way leads to a universe with its own unique set of physical laws. This collection of possible universes is known as the string theory landscape, and its estimated size is staggering, with some calculations suggesting 10 to the power of 500 possibilities. This presents a quiet disaster for a scientific theory. A theory that can predict almost anything predicts, in practice, almost nothing. If one of these many universes happens to match ours, what have we really learned? It makes it difficult to test the theory, because it has more possible outcomes than there are atoms in the known universe. This leads to the third and, for many, the most significant challenge. String theory has not yet made a single, unique, falsifiable prediction in 50 years of development. Science is a process of testing ideas against observation. A theory must make a concrete prediction that can be checked with an experiment. If it's right, the theory is strengthened. If it's wrong, it is set aside. String theory has so far been difficult to test in this way. Its ideas, like extra dimensions, seem to lie at energy scales far beyond what our instruments can reach. So we are left in a strange, quiet place. We have a beautiful and powerful mathematical structure that seems to solve the deepest problem in physics, but it exists in a theoretical world we cannot yet touch or see. It remains a hope, not yet a discovery. And the quiet conflict continues. A quiet shift. So where do we find ourselves? We began with two nearly perfect descriptions of the large and the small. We found that when they meet, their stories conflict, producing a quiet signal of infinity that tells us our understanding is incomplete. We then looked to the most promising idea, string theory, only to find it has been wandering in a mathematical landscape for half a century, unable to make clear contact with the observable world. It can feel like physics has reached a dead end. But perhaps that is the wrong way to look at it. Perhaps this infinity in our equations is not a flaw, but a message. Nature is quietly telling us that some of our foundational assumptions may be incorrect. It is pointing to the gap in our knowledge and inviting us to look more deeply. This is not an end, it is a signpost, pointing toward a new way of thinking. And while the grand story of string theory has stalled, something else has begun to happen. In quiet labs and on blackboards around the world, new ideas are emerging. They suggest the solution might not come from one single, grand theory, but through smaller, more tangible paths. One interesting path involves a second look at older ideas. Some theories, like quadratic gravity, were proposed decades ago but were set aside because of difficult mathematical problems. Recently, physicists have begun to revisit these ideas with new tools. Some of this work explores a concept called asymptotic safety, a non-perturbative approach to quantum gravity. The hope is that in a more complete version of the theory, gravity might behave differently at extremely high energies, perhaps growing weaker, which could prevent the troublesome infinities from appearing at all. It suggests that a solution might have been hiding in an idea we had long ago moved past. Even more exciting is the idea that we might not have to wait for a perfect theory to begin testing the quantum nature of gravity. For decades, it was assumed that seeing these effects would be impossible. But that idea is now being challenged. Physicists have proposed ingenious tabletop experiments that could bring the question into our laboratories. One such proposal involves a mind-bending application of quantum mechanics. The idea is to take a tiny, nanometer-sized diamond and place it into a quantum superposition, putting it in two places at once. By carefully measuring how this quantum mass interacts gravitationally, it might be possible to detect the subtle quantum nature of gravity itself. While these experiments are incredibly difficult and at the very edge of our current abilities, they represent a shift in thinking. For the first time, the question of whether gravity is truly quantum is becoming something we might be able to answer empirically. This shift from pure theory toward technology is already happening. NASA, in partnership with the company Inflection, is developing a quantum gravity sensor to be used in space. Using clouds of ultra-cold atoms, this device will measure tiny variations in Earth's gravitational field with incredible precision. While its primary goal is to map things like ocean currents and underground water reserves, it represents a monumental step. We are building tools that operate on the very principles we are trying to understand, bringing the abstract quest for quantum gravity closer to the world of real technology. So, where does this leave us? The single, unified equation has not been found. The infinity at the heart of physics remains, a quiet reminder of what we don't yet know. But the story is not over. The feeling in physics is shifting from one of frustration to one of renewed, quiet excitement. The infinity in our equations is not a stop sign. It is a starting point. It has forced us to ask deeper questions. Is spacetime truly fundamental, or does it emerge from something else? Is the universe continuous, or is it, as quantum mechanics suggests, fundamentally discrete? We are on the cusp of a new understanding, and the quest to resolve that single, impossible number, to finally write the story that explains it all, remains one of the most profound and beautiful adventures in human thought. This journey to solve a quiet puzzle is happening right now. New ideas are being explored, and new experiments are being designed that could change how we see our universe. If this kind of calm exploration into science helps you unwind, consider subscribing to the channel. But I'm genuinely curious to hear your thoughts. We've talked about the limits of our current theories and the unproven hope of new ones. What do you think is the missing piece of the story? Is it a new understanding of gravity, a new principle we haven't discovered yet, or something else entirely? Feel free to share what you think in the comments below. And if you enjoyed this quiet dive into the foundations of physics, you might also like our video exploring the cosmological constant problem, which takes this story of infinity to an even more perplexing place. The glitch in the universe where all physics breaks. There are places in the universe where our understanding seems to pause. Not just for a person, or a planet, or even a star, but for the rules of reality as we know them. Places where our most familiar ideas about space, time, and matter quietly unravel. These are not distant, philosophical concepts. They are real, scattered across the cosmos, often hidden behind an impenetrable quiet. At the center of a black hole lies one of these places. A point where gravity becomes so strong that our equations no longer offer clear answers. For a long time, this point, the singularity, has been a challenge for physics, a place where our mathematics points toward infinity, a result that often signals an incomplete story. But what if this isn't an ending? What if it is simply a signpost? A quiet clue, pointing toward a deeper, more fundamental truth about the fabric of the cosmos. The story of the singularity is, in a way, the story of how a challenge in our understanding has led to one of the most profound quests in science. The search for a single theory to describe everything. Following this one clue could reshape what we think we know about space and time, from the first moments of the universe to its eventual fate. This is the story of that place where our physics pauses, and why resolving it with a strange new idea called quantum gravity could change how we see the world. Imagine you are drifting in the silent expanse of space. Before you hangs a sphere of pure blackness, a hole in the fabric of the starlight. It does not glow or shine, it only absorbs. The light from distant galaxies bends around its edge, distorted into a halo of quiet, warped light. This is the event horizon, the point of no return. To someone watching from a safe distance, your fall would seem to take a very long time. They would see your image slow, stretch, and fade until you become a static, frozen shape on the edge of that darkness. But for you, time would feel normal. You cross an invisible line, with no bump or wall to mark the passage. At that moment, your fate has been sealed. From here, every possible path leads to one place, the center. And what is waiting there is not just the end of a journey, but the edge of physics as we know it. The anatomy of a cosmic structure. To understand this puzzle, we first have to understand the object that holds it. What is a black hole? The answer begins, as many stories in the cosmos do, with the end of a star's life. For millions, or even billions, of years, a massive star exists in a delicate balance. In its core, the immense inward pull of its own gravity is held off by the outward pressure of nuclear fusion. Lighter elements are forged into heavier ones in a stellar furnace that can outshine entire galaxies. This process is the star's life. But it cannot last forever. Eventually, the star's fuel begins to run out. The fusion process slows, and then it stops. Suddenly, the outward pressure fades, and the balance is broken. Gravity, the quiet, persistent force that has shaped the star its entire life, finally takes over. The star's core collapses inward in less than a second. If the star is massive enough, at least 20 or 30 times the mass of our own sun, nothing known to physics can stop this collapse. The atoms in the core are pressed together with such force that their structure gives way. Protons and electrons merge into a sea of neutrons. If the collapse were to stop here, it would form a neutron star, an object so dense that a single spoonful of it would weigh more than a mountain. But for the most massive stars, even this is not the end. The collapse continues relentlessly. The neutrons themselves are overcome by a gravitational pull so extreme that it yields to no other force. The star's mass continues to shrink, collapsing past any imaginable density, toward an almost unthinkable state. A point of nearly zero size containing an immense mass. This is how a black hole is formed. As the core shrinks, its gravitational field grows stronger. Imagine space-time as a stretched sheet of fabric. A planet like Earth creates a small dip. A star creates a deeper one. But the collapsing core of this star creates a well so deep that it seems to have no bottom. At a certain point, the slope becomes so steep that the speed needed to climb out of it becomes greater than the speed of light. This boundary is the event horizon. It is not a physical surface you could touch, but rather a one-way door in space-time. Anything that crosses it, light, matter, information, can no longer leave. It is pulled toward the center. From the outside, the region inside the event horizon appears as a perfect sphere of blackness, its size determined only by its mass. We have seen these shadows against the cosmos. In recent years, the Event Horizon Telescope has captured images of the supermassive black holes at the center of our own galaxy and the distant galaxy M87, confirming predictions made by Albert Einstein's theory of general relativity over a century ago. Einstein's theory describes these objects with remarkable accuracy. It explains how they bend light and warp time. For everything happening outside the event horizon, general relativity is a perfect guide. But this elegant theory also carries the seeds of its own limit. Because if you ask general relativity what happens at the very center, it gives an answer that doesn't seem to make sense. It gives you the puzzle. It gives you the singularity. The journey toward infinity. Let's return to our journey. We've crossed the event horizon and are now inside the black hole. What happens next? From this point on, the relationship between space and time changes. Outside the black hole, you can move freely through space but are always carried forward in time. Inside, that logic flips. The pull toward the center is so absolute that the direction, toward the singularity, becomes as inevitable as the future. You can no more stop your movement toward the center than you could stop time itself. The singularity is no longer just a place in space, it is a moment in your future. Your final moment. You would not arrive there in one piece. General relativity paints a strange picture of your final seconds. The force of gravity you would experience would not be uniform. The part of your body closer to the center would be pulled much more strongly than the part that is farther away. If you were falling feet first, your feet would be pulled with far greater force than your head. This difference, known as a tidal force, would stretch your body, elongating it. At the same time, you would be compressed from the sides. This process is sometimes called spaghettification, and it would separate your body into its constituent atoms long before you reached the center. This stream of particles would then continue its one-way journey. But what is the center itself? What is this singularity that everything is moving toward? According to Einstein's equations, it is a point of zero volume. All the mass of the collapsed star, a mass that could be millions of times greater than our Sun, is compressed into a space that is infinitely small. Here, we have to pause at the word infinite. In physics, infinity is not just a very large number. It is often a quiet signal. It suggests not an answer, but the place where a new question must be asked. The prediction of a singularity is one of the most profound signals that a theory has reached its limit. Think of density. Density is mass divided by volume. If you have a finite mass and divide it by a volume of zero, the result is infinite density. The equations also predict that the curvature of spacetime becomes infinite. The fabric of the universe is no longer just curved, it is punctured. A measure of this curvature, the Kretschmann scalar, goes to infinity, confirming that the theory is describing a physically implausible state. It's a sign that the laws of physics, as we currently write them, have stopped. This isn't just a theoretical curiosity. The work of Roger Penrose and Stephen Hawking showed that, according to general relativity, singularities are an unavoidable result of gravitational collapse. If general relativity is the complete story of gravity, then these places must exist. For decades, this was the accepted, if unsettling, picture. A point where our knowledge ends. But this leads to an even deeper puzzle, a quiet conflict at the heart of modern physics. Two descriptions of the universe. The 20th century gave us two remarkable ways of describing the universe. One describes the world of the very big, planets, stars, galaxies, and the force of gravity that shapes their movements. This is Einstein's general theory of relativity. It views spacetime as a smooth, continuous fabric, bent and warped by mass and energy. Gravity, in this view, is the shape of that fabric. It is a theory of elegant, deterministic curves. The other theory describes the world of the very small, atoms, electrons, and the other particles that make up reality. This is quantum mechanics. It paints a very different picture. In the quantum realm, things are not smooth and continuous. Energy comes in discrete packets, or quanta. Particles exist as clouds of probability rather than indefinite locations. The world is fuzzy, uncertain, and grainy. It is a theory of jittery, quantized pieces. These two theories are the foundations of modern physics, and both are incredibly successful. General relativity predicts the orbits of planets and the existence of gravitational waves. Quantum mechanics allows us to build lasers and computers and is the most precisely tested theory in all of science. There's just one challenge. The two theories are deeply, fundamentally incompatible. Physics describes three of the four fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force, using quantum mechanics. These forces are all quantized, meaning they are described by the exchange of tiny particles. Even when the equations for these forces produced infinities, physicists developed a technique called renormalization to manage them, allowing for fantastically precise predictions. But gravity is the exception. According to Einstein, gravity is the geometry of spacetime. To quantize gravity, you would need to quantize spacetime itself. Every attempt to do so has led to a problem. The equations produce uncontrollable infinities, and the technique of renormalization does not work. For most of the universe, this isn't an issue. On the scale of planets, quantum effects are too small to notice. On the scale of atoms, gravity is too weak to matter. You can use one theory for the big and the other for the small, and they never need to interact. But in a black hole, these two worlds meet. A black hole is both incredibly massive, the domain of relativity, and, at its center, incredibly small, the domain of quantum mechanics. To describe the singularity, you need a single theory that can handle both gravity and quantum effects at the same time. You need a theory of quantum gravity. We don't have one yet. And that is the heart of the puzzle. The singularity is not just a limit of one theory. It is the place where our two greatest descriptions of the universe arrive together, and both fall silent. It is the clearest signal in all of physics that our understanding is incomplete, and that these two ideas must be part of a single, deeper story. The search for a deeper story. The breakdown of physics at the singularity is not an endpoint, it is an invitation. It suggests that beneath both relativity and quantum mechanics, there must be a more fundamental layer of reality. Finding this theory of quantum gravity is one of the great open questions of modern physics. It would not just solve the puzzle of the singularity, it would likely answer other deep questions, like what happened at the Big Bang and what the true nature of spacetime is. For decades, some of the most dedicated minds in science have worked on this problem. While a final, proven theory has not yet emerged, several promising ideas have. They offer different pictures of what might be happening at the center of a black hole, replacing the infinite puzzle with something else, something perhaps even more strange and wonderful. Idea 1. Loop quantum gravity and the cosmic bounds. One of the leading ideas is called loop quantum gravity, or LQG. This theory takes the quantum concept of discreteness and applies it to spacetime itself. In LQG, the smooth fabric of spacetime from Einstein's theory is just an approximation. If you could zoom in to an impossibly small scale, the Planck scale, you would find that spacetime is not smooth at all. It is made of something. LQG proposes that spacetime is woven from a network of indivisible loops. There are atoms of space, tiny quantum volumes that cannot be divided further. There is a smallest possible size, a fundamental pixelation of reality. This one simple idea changes everything. If there is a minimum possible volume, you can never crush matter down to a point of zero volume. The collapse of the star doesn't end at an infinitely dense singularity. Instead, as the matter is squeezed down toward the Planck scale, it reaches the fundamental graininess of spacetime itself and can be compressed no further. So, what happens instead of a singularity? It bounces. In this picture, the collapsing matter reaches a state of unimaginable but finite density, forming something called a Planck star. Then, quantum gravity effects create a powerful repulsive force that halts the collapse and causes the matter to rebound outward. This bounce might create a new, expanding region of spacetime on the other side, perhaps a bridge to another part of our universe or even a new baby universe. The black hole becomes a kind of gateway. What falls in is effectively reborn. This idea replaces the breaking of laws with a transformation governed by new ones. Idea 2. String theory and the fuzzball. The other main approach is string theory. It begins with a different premise, that the fundamental building blocks of the universe are not particles, but tiny, one-dimensional vibrating strings. Everything we see, electrons, photons, quarks, is just a different note played by these strings. A string vibrating in one way appears to us as an electron, another vibration appears as a photon. And, importantly, one particular vibration pattern corresponds to the graviton, the long-sought quantum particle of gravity. So, what does string theory say about black holes? The picture it paints is just as strange. According to some string theorists, when a star collapses, the matter doesn't get crushed into a single point. Instead, as the energy grows, the fundamental strings that make up the matter tangle and vibrate together. The result is that the singularity is replaced by a complex, vibrating mass of strings, sometimes called a fuzzball. This object would fill the entire volume within the event horizon. From the outside, it would look and act exactly like a black hole described by general relativity. But on the inside, there would be no empty space and no infinite point, only this complex, stringy structure. This idea also offers a potential solution to another puzzle known as the information loss paradox, suggesting that information isn't destroyed but is instead stored in the complex surface of the fuzzball, to be slowly released over time. Loop quantum gravity and string theory are the most explored paths, but they are not the only ones. Physicists are working on many other ideas. What they all share is the goal of resolving the singularity. They all seek to replace the infinite puzzle with new, finite physics, to write the chapter of the story that general relativity left blank. The puzzle is a beginning. The implications of solving this puzzle are immense. It reaches far beyond just understanding black holes. It touches on the very origin of our own cosmos. The Big Bang, our best theory for the origin of the universe, also begins with a singularity. It suggests that 13.8 billion years ago, the entire observable universe was contained within an infinitely hot, infinitely dense point. Just like the black hole singularity, this is a place where our current laws of physics fall silent. A successful theory of quantum gravity would, therefore, also resolve the Big Bang singularity. It could tell us what truly happened at the moment of creation. Was it a big bounce, as some theories suggest, where a previous universe collapsed and rebounded to become our own? This would imply a cyclic cosmos with no true beginning or end. Or perhaps an even more remarkable idea is true. Some physicists have proposed that our universe could be the result of a black hole forming in a higher dimensional parent universe. In this scenario, our Big Bang was not the start of everything, but simply the moment something in another cosmos collapsed and was reborn as our universe. This quest is no longer confined to chalkboards. For the first time, the frontier of quantum gravity is slowly moving toward the laboratory. In a recent experiment, scientists managed to measure the tiny gravitational pull on a particle so small that its behavior is governed by quantum mechanics. These are the very first steps, but they represent a slow shift from pure theory to experimental science. We are beginning to build the tools to ask the universe these questions directly. So we find ourselves at the edge of our own understanding, looking into a profound quiet. The singularity, the puzzle at the heart of every black hole, has for a century represented a boundary. A point of infinite density and infinite uncertainty. But now, we are beginning to see it differently. It is not an end. It is a guide. It is perhaps the most powerful clue the universe has given us that our picture of reality is not yet complete. It encourages us to search for a deeper theory, one that can unite the world of the very large with the world of the very small. Whether the answer is a bouncing universe, a complex tangle of strings, or an idea we haven't yet imagined, one thing feels clear: solving the puzzle is key. The path to a more complete theory of everything runs directly through the heart of a black hole. The equations that finally describe what happens in that impossible place will likely be the same ones that describe the birth of our universe. The puzzle is not a breakdown of physics. It feels more like the beginning of a revolution in our understanding. The journey to understand these quiet, cosmic puzzles is far from over. It pushes us to question the nature of space, time, and reality itself. So, I have a question for you. Do you think these places are simply physics we don't understand yet, a puzzle that will one day have a clear answer? Or are they a hint of something even stranger, a sign that the fabric of our reality is not what it seems? I'd be interested to read your thoughts in the comments below. The quest to resolve the singularity is a quiet testament to the human drive to understand the cosmos. It's a journey that has taken us from Einstein's elegant equations to the strange landscapes of quantum reality. And while the final answer remains hidden, we are closer than ever to seeing behind the veil. The next generation of telescopes and experiments may provide the crucial clues needed to move forward, finally revealing what truly lies at the heart of these structures. The universe has left us a trail of breadcrumbs, and it leads straight into the beautiful, quiet darkness of a black hole. And we seem determined to follow it. The quantum glitch that created our universe. We exist in an ocean of galaxies. A cosmic web of 100 billion star systems, each holding 100 billion suns, stretching across distances so vast they feel separate from our understanding. For as long as we have looked up, we have asked, where did all of this come from? The story most of us know is the Big Bang. We are told that around 13.8 billion years ago, the entire universe, all of space and time, all matter and energy, emerged from a single, impossibly dense point. But this is not the whole story. In fact, it tells us something that appears to be wrong. The simple, explosive Big Bang you learned about should have created a universe that was perfectly smooth. A featureless soup of particles, expanding quietly into the dark. It should have been a universe with no structure. No galaxies, no stars, no planets, and no us. And yet, we are here. This complex, structured cosmos exists. The question is why. The answer, physicists now believe, is a glitch. A tiny, random hiccup in the fabric of reality itself, in the very first moments of time. This is the story of that quantum glitch. It's a story of how a flicker of uncertainty in a pre-cosmic nothing became the seed for everything we see. This is a journey to the absolute edge of known science, to a place where our most fundamental laws seem to break down, and where the universe's deepest secret is still waiting to be understood. A universe of clues. Every scientific story begins with the evidence, and our universe has left a trail of clues stretching back billions of years. To understand the story, we first need to look at those clues. The primary piece of evidence is the Big Bang itself. The idea did not come from a sudden insight, but from careful observation. In the 1920s, astronomers like Edwin Hubble pointed their telescopes toward distant galaxies and noticed something strange. The light from nearly every galaxy was stretched, or redshifted. More than that, the farther away a galaxy was, the more its light was stretched. The conclusion was stunning. The space between galaxies is expanding. The universe is growing. This was a revolution in thought. If the universe is expanding today, it means that yesterday, it must have been smaller. And the day before that, smaller still. If you run the cosmic movie in reverse, all the matter and energy in the universe get closer and closer, until they are squeezed into an unbelievably hot, dense state. This initial state is what we call the Big Bang. This is not just an idea, it is backed by multiple, independent lines of evidence. The first is the expansion we just discussed. The second is the chemical makeup of the universe. When we look out at the oldest stars and gas clouds, we find they are made of about 75% hydrogen and 25% helium. These are exactly the proportions you would expect to be cooked up in the furnace of a hot, dense early universe, long before stars had a chance to form heavier elements. But the most important piece of evidence is a faint, persistent glow of light that comes from every direction in the sky. It is the oldest light in the universe. It is called the cosmic microwave background, or CMB. To understand it, imagine the early universe. For the first 380,000 years, it was so hot and dense that atoms could not form. It was an opaque fog of free protons and electrons that trapped light. Any photon of light was immediately scattered, like headlights in a thick fog. But as the universe expanded, it cooled. Once the temperature dropped to about 3000 Kelvin, something crucial happened. Protons and electrons could finally bind together, forming the first stable hydrogen atoms. Suddenly, the fog lifted. The universe became transparent. The photons that were bouncing around were set free, and they have been traveling through space, unimpeded, ever since. That light is the cosmic microwave background. It is a baby picture of the universe when it was just 380,000 years old. When it was first detected by accident in 1964, we were seeing the echoes of creation. This light is our most precious artifact. It is a direct window into the conditions of the early universe. And when we look at it closely, this is where the deeper story truly begins. The uniformity paradox. When scientists built satellites like COBE, WMAP, and Planck, they created incredibly detailed maps of the cosmic microwave background. What they found was astonishing. The temperature of this ancient light is almost perfectly uniform across the entire sky. It is 2.725 Kelvin, just a few degrees above absolute zero, no matter where you look. The variations are minuscule, only about 1 part in 100,000. At first, this smoothness seems to confirm the simple Big Bang model. But it actually reveals a profound problem. In fact, it reveals two. The first is known as the horizon problem. Think back to the universe at 380,000 years old. 2 points on opposite sides of the sky in that baby picture were separated by a distance much greater than light could have traveled in that time. There was no way for them to have exchanged heat to even out their temperatures. It would be like finding 2 rooms on opposite ends of a giant castle that are the exact same temperature, even though they were never connected. So how did they coordinate to be so perfectly alike? The simple Big Bang theory has no answer. The universe is too smooth. But this leads to a second, even deeper problem. The universe is almost perfect, but not quite. Those tiny 1 in 100,000 variations are there. And it is a good thing they are. If the universe had been perfectly smooth, it would have stayed that way. Gravity needs something to grab onto. A perfectly uniform cloud of gas will just expand and thin out. There would be no initial clumps of matter to act as seeds. No places just slightly denser than average, where gravity could begin the slow process of pulling more matter in. Without those tiny imperfections, gravity would have been powerless. There would be no galaxies, no stars, no planets, and no one to wonder about it. So here is the central paradox. The universe is far smoother than it should be, yet just lumpy enough for us to exist. The smoothness presented a puzzle, but the tiny imperfections held the key to our own existence. The simple Big Bang could explain a smooth universe, but it could not explain why we are here. A new chapter in the story was needed. Cosmic inflation. In the early 1980s, a physicist named Alan Guth was wrestling with this very problem. He proposed a radical idea, a modification to the very beginning of the story. An idea called cosmic inflation. Inflation theory proposes that in the first fraction of a second, between roughly 10 to the minus 36 and 10 to the minus 32 seconds, the universe underwent a period of mind-bogglingly rapid, exponential expansion. It was not just expanding, it was expanding faster than light. This does not violate Einstein's theory of relativity. Nothing can travel through space faster than light, but space itself can expand at any speed. During this inflationary epoch, a region of space far smaller than a proton would have ballooned to become larger than our entire observable universe today. This incredible stretching has a profound effect. Imagine you have a tiny, wrinkled balloon. If you suddenly inflate it to the size of the Earth, those wrinkles would be stretched out so completely that any patch you looked at would appear flat and smooth. This is what inflation does to the universe. It solves the horizon problem. The two distant points on opposite sides of our sky were in contact, right next to each other, before inflation kicked in and violently flung them apart. They have the same temperature because they started in the same tiny neighborhood. Inflation was a brilliant solution. It explained why the universe is so incredibly uniform. But in explaining the smoothness, inflation appeared to create an even deeper problem. If inflation is so good at smoothing everything out, it should have left the universe perfectly, absolutely smooth. It explains the uniformity, but it still doesn't explain the imperfections that allowed for our existence. To find the origin of those imperfections, the glitch that made us, we have to leave the world of the very big and journey into an entirely different realm of physics. We have to go quantum. The buzzing void. One of the most profound discoveries of the 20th century was that empty space is not empty at all. On the scale of our everyday lives, a vacuum is just nothing. But if you could zoom in, down to the impossibly small scales of quantum mechanics, you would find a seething, chaotic reality. This world is governed by a set of rules called quantum field theory. The theory says the universe is permeated by invisible fields, an electromagnetic field, an electron field, and so on. A particle is just a localized vibration in its corresponding field. You can think of a quantum field like the surface of a perfectly still pond. If you tap the surface, you create a ripple. That ripple is a particle. But this quantum pond is never perfectly still. It is constrained by one of the most fundamental laws of nature, the Heisenberg uncertainty principle. Werner Heisenberg discovered that you cannot know certain pairs of properties, like a particle's position and its momentum, with perfect precision at the same time. It is not a limitation of our instruments, it is a fundamental fuzziness baked into the fabric of reality. This principle also applies to energy and time. Over very short periods, energy can appear from nowhere, as long as it is paid back very quickly. So our quantum pond is actually a roiling, bubbling soup. Tiny ripples are constantly, randomly appearing and disappearing. These are quantum fluctuations. For fleeting moments, a blip of energy can create a pair of virtual particles, a particle and its antiparticle, which almost immediately annihilate, vanishing back into the nothing from which they came. The vacuum of space is a storm of these phantom particles. This is not a theoretical fantasy. We can measure its effects. In an experiment called the Casimir effect, two uncharged metal plates in a vacuum will be pushed together by the pressure of more virtual particles on their outside than in the tiny gap between them. This buzzing void is a real, fundamental feature of our universe. Under normal circumstances, these fluctuations are microscopic and fleeting. But in the first moment of the universe, they were the main event, stretching a glitch to cosmic size. Now, these two seemingly separate ideas come together. On one side, cosmic inflation, the theory that makes the universe incredibly smooth. In the other, quantum fluctuations, the principle that ensures nothing is ever perfectly smooth. Together, they resolve the paradox. Let us go back to that first sliver of a second. The universe is an unimaginably dense quantum soup. The quantum fields that fill this tiny space are buzzing with energy, fluctuating wildly. Then, inflation kicks in. As space itself starts to stretch, it grabs hold of these tiny, virtual fluctuations. Instead of letting them disappear, inflation stretches them out violently. A microscopic, subatomic ripple is blown up to astronomical proportions. These fluctuations, which would have vanished in a trillionth of a second, were stretched so rapidly that they were effectively frozen into the fabric of spacetime. The rapid expansion pumped so much energy into them that they became real, permanent features. These are the quantum glitches. These are the seeds. What began as a random, probabilistic hiccup at the quantum scale became a real, macroscopic variation in the energy density of the early universe. Some regions ended up with slightly more energy, and some with slightly less, all because of a roll of the quantum dice in that first instant. This is the synthesis that forms the core of our modern origin story. Inflation explains why the universe is so smooth, but the quantum uncertainty principle explains why it is not perfectly smooth. These imperfections were not a mistake. They were the very reason anything exists at all. The fingerprints of creation. A theory, no matter how elegant, is just speculation without evidence. The theory of inflation and quantum fluctuations makes a very specific, testable prediction. It predicts that the fingerprints of these glitches should be visible today, imprinted on the cosmic microwave background. The stretched-out fluctuations would have created a specific pattern of slightly hotter and cooler spots in the primordial plasma. When the universe became transparent, the light that was released carried a snapshot of those temperature variations with it. For decades, cosmologists worked to build instruments sensitive enough to see them. First came the COBE satellite in 1992. It produced the first, blurry map of the CMB, and the fluctuations were there. The team leader, George Smoot, famously said, "If you're religious, it's like looking at God." What he meant was that they were looking at the primordial seeds of creation. Then came the WMAP probe in the 2000s, and later, the Planck spacecraft in the 2010s, which provided a map of such stunning precision it has become the benchmark for modern cosmology. What these maps show is a triumph for the theory. The pattern of hot and cold spots in the CMB is a near-perfect match for the predictions made by the model. We are, quite literally, seeing the macroscopic evidence of quantum mechanics written across the sky. These maps are photographs of the quantum glitches that created our universe. Every galaxy cluster, every star system, owes its origin to one of those tiny, randomly generated spots on that map. The evidence is so compelling that this picture has become the standard model of cosmology. The unsolved case. Our story seems to have reached a satisfying conclusion. We have the glitch, the mechanism of inflation, and the evidence in the CMB. And yet, our understanding comes to a stop at the most critical moment. Our entire story begins a tiny fraction of a second after the beginning. What happened at time equals zero? Here, our two most successful theories of reality collide, and the laws of physics as we know them break down. On one side, we have Einstein's general theory of relativity, the rulebook for the very large. Run backward, its equations predict a point of infinite density and temperature, a singularity. On the other side, we have quantum mechanics, the rulebook for the very small. Quantum mechanics tells us that things are fuzzy and probabilistic, and it does not permit infinities. At the very beginning, the entire universe was squeezed into a space smaller than an atom. This is a situation of immense gravity on an infinitesimally small scale. To describe this state, you need to unite both theories. You need a theory of quantum gravity. And we do not have one. When you try to combine the equations, the math breaks. It is the most famous problem in all of physics. What happened at the singularity? What created the quantum glitch in the first place? We cannot answer these questions because our physics fails us precisely where we need it most. To solve this, we need a new kind of physics. The next frontier. The search for a theory of quantum gravity is the quiet frontier of modern physics. It is the effort to write a single set of laws for the universe at all scales. There are several promising candidates. One is string theory. It proposes that the fundamental constituents of reality are not particles, but tiny, vibrating strings. Different vibrations produce different particles, like notes on a guitar. The theory is mathematically elegant, but it requires extra, hidden dimensions and has proven difficult to test. Another approach is loop quantum gravity, or LQG. Here, spacetime itself is not smooth, but woven from a network of finite, indivisible loops. There is a smallest possible volume. Because of this, you cannot squeeze the universe to an infinitely small point. The singularity is avoided. Instead, some LQG models predict a big bounce, where our universe emerged from the collapse of a previous one. Research into LQG is very active, with conferences and schools planned well into 2026. More recently, radical ideas like a post-quantum theory of classical gravity have been proposed. It suggests that perhaps gravity is not quantum at all, and that quantum mechanics itself needs to be modified. The problem with all these theories is the lack of evidence. The energies required to probe this realm are 1 trillion times higher than what our most powerful particle accelerators can achieve. So, physicists look for subtle clues hidden in the cosmos, like specific signatures in the cosmic microwave background that could only have been produced by one theory and not another. The universe itself is our only laboratory. The glitch that made us. So, where does this journey leave us? We have traveled from the familiar sight of galaxies back through 13.8 billion years, to the very edge of time. We have found that the story of our universe is one of a paradox, born too smooth, yet just lumpy enough to exist. We have found the solution in a stunning marriage of the very large and the very small. A moment of exponential expansion made the universe vast and uniform, but it was the inherent uncertainty of the quantum world that provided the crucial imperfection. A random, probabilistic glitch, stretched to cosmic proportions, became the seed for everything. We have seen the evidence for this story written in the faint afterglow of creation. And yet, we find ourselves at a new frontier. At the moment of creation, our knowledge ends, pointing to a deeper level of reality we have yet to grasp. There is something quietly humbling about this realization. When you look up at the night sky, you are not looking at the product of some perfect, deterministic blueprint. You are staring at the large-scale consequence of a random, quantum accident. The universe, it seems, was not written in stone. It was born from a possibility, a statistical fluke. And the fact that we are here, as products of that very glitch, able to look back and piece together this astonishing story, is perhaps the most remarkable thing of all. Trying to see the smallest thing creates a black hole. There is a quiet and persistent human habit of looking closer. It is a journey that has carried us from looking at the stars with our own eyes to seeing the faint, ancient light of the early universe. It has taken us from wondering what we are made of, to observing the very machinery of life. Each time we have built a new tool to see more deeply into nature, new worlds have appeared: cells, atoms, quarks, and fields. This is a story about that same quiet curiosity, but it is also about where that journey finds its end. What if the quest to see smaller has a final frontier? Not a limit of technology or imagination, but a fundamental boundary woven into the fabric of reality itself. A point where the universe quietly and firmly says, "No further." This is not a philosophical guess. It is a conclusion that emerges when two of our most important ideas meet: Einstein's description of gravity and the strange, subtle rules of quantum mechanics. It is the story of a thought experiment, the most powerful microscope that could ever be imagined, designed for one purpose: to see the smallest possible thing, the fundamental texture of reality. And it is a story that ends not in a sudden catastrophe, but in a profound and unavoidable silence. Imagine you could build that microscope. Not a machine of glass and metal, but one of pure energy, able to focus on a single, tiny point in empty space. What would you see? The smooth, continuous fabric of spacetime that Einstein described? Or would it be something else, a granular, pixelated reality? The very act of looking at that point would concentrate so much energy into such a small space that it would create a black hole, quietly and completely sealing off the very thing you wished to see. Physics suggests that trying to observe the smallest part of the universe is a self-defeating act. And the reason for this reveals a deep secret about how reality is put together. It is not a failure of our tools, but a simple, unchangeable rule of the cosmos. The foundation of seeing. To understand this strange prediction, we first have to understand the simple principle behind seeing anything at all. Whether it is your eyes perceiving these words or a biologist studying a cell, the method is the same. To see something, you must illuminate it. You have to bounce something off of it, usually a particle of light, a photon. Think of it like trying to learn the shape of an object in a dark room by gently throwing very small bouncy balls at it. If you are trying to find something large, like a chair, the balls will bounce back to you, and you can slowly build a picture of its location and form. But now imagine there is a tiny marble on the floor. If you keep using the same bouncy balls, they will likely roll right over the marble, their paths barely disturbed. The marble is too small to have a meaningful effect on the much larger ball. To find the marble, you need a smaller probe. The probe must be small enough that it will be noticeably deflected when it makes contact, revealing the marble's presence. In physics, the size of your probe is the wavelength of the light you use. Light is a wave, and the distance between its crests is its wavelength. To resolve, or see, an object, the wavelength of the light must be smaller than the object itself. Trying to use a long wavelength radio wave to see a bacterium is like throwing a beach ball to find a grain of sand. The wave simply passes over it, unaware it was ever there. For this reason, the history of microscopy has been a quiet search for shorter and shorter wavelengths. Early optical microscopes, which use visible light, were revolutionary. They opened up the microbial world. But they reached a limit. The wavelength of visible light is between 400 and 700 nanometers. This is incredibly small, but it is enormous next to an atom. No matter how perfect the lenses, you cannot see a single atom with visible light. The waves are simply too long, they wash over it. To see smaller, we needed a new kind of illumination. In the 20th century, we found one: the electron. Because of the rules of quantum mechanics, particles like electrons also behave as waves. And importantly, the wavelength of an electron can be controlled by its energy. The more energy you give it, the shorter its wavelength becomes. This led to the invention of the electron microscope. By accelerating electrons to high energies, scientists created light with wavelengths thousands of times shorter than visible light. Slowly, the world of the very small opened up. We could see viruses, then the proteins inside our cells, and eventually, with other related techniques, we could resolve the soft outlines of individual atoms. The rule held: to see smaller things, you need probes with shorter wavelengths. And shorter wavelengths mean higher energy. The energy of a photon is inversely proportional to its wavelength. A long wavelength radio photon is a low-energy particle. A short wavelength ultraviolet photon carries more energy, which is why it can cause a sunburn. An even shorter X-ray photon is more energetic still. And gamma-ray photons, with the shortest wavelengths we often see, are the most energetic of all, created in violent cosmic events. Our path forward seems simple. To see smaller, we just need to increase the energy. We went from visible light to electrons. We can use gamma rays. We can imagine particle beams with energies far beyond anything produced on Earth. So, what stops us from turning up the energy indefinitely, shortening our wavelength to an infinitesimal size, and finally seeing what reality is truly made of at its deepest level? This is where our journey takes an unexpected turn. As we increase the energy, we begin to wake a quiet giant that has been negligible until now: gravity. And here, our story moves from the familiar world of microscopes to the strange and subtle realm of Einstein and black holes. Reaching for the smallest scale, let us imagine our experiment. We can call it the ultimate microscope. It is not a physical device, but an exercise in thought. Its purpose is simple: to resolve a region of space smaller than anything ever seen. We want to focus on a single point to see what is there. Following our rule, to see something incredibly small, we need a probe with an incredibly short wavelength. This means our probe must have a truly immense amount of energy. We are not talking about the energy of a light bulb, or even a powerful particle accelerator like the Large Hadron Collider. We are talking about energies that are difficult to picture. We want to probe a distance known as the Planck length. The Planck length is a scale of distance that is mind-bogglingly small. It is about 1.6 times 10 to the minus 35 meters. That is a decimal point followed by 34 zeros. If you were to scale up a single atom to be the size of the entire observable universe, the Planck length would be about the height of a tree. It is the scale where our current understanding of physics is expected to break down. It is the domain where the smooth, predictable world of Einstein's gravity meets the uncertain, probabilistic world of quantum mechanics. So, our ultimate microscope is aimed at a target the size of the Planck length. What energy does our probe need? The answer comes from a pillar of quantum theory: the Heisenberg uncertainty principle. The uncertainty principle states that you cannot know both the exact position and the exact momentum of a particle at the same time. There is a fundamental trade-off. The more precisely you measure a particle's position, reducing the uncertainty increment x, the less precisely you can know its momentum, meaning the uncertainty increment p grows. This is not a limitation of our equipment. It is an inherent fuzziness built into the universe itself. When we say we want to resolve a region of space the size of the Planck length, we are really saying that we want to confine our probe, a single, super-energetic photon, to that tiny region. We want the uncertainty in its position, increment x, to be no larger than the Planck length. According to Heisenberg, if we squeeze the uncertainty in position down to this impossibly small value, the uncertainty in the photon's momentum must become enormous. And since a photon's momentum is directly related to its energy, this means the energy of our probe photon must be gigantic. How gigantic? The energy required is called the Planck energy. It is about 10 billion times higher than the energy of collisions at the Large Hadron Collider. It is roughly equivalent to the energy released by several hundred kilograms of TNT. And here is the crucial point. Our thought experiment requires that we take all of that immense energy and concentrate it into a space no larger than a single Planck length. We are not just creating a high-energy particle. We are creating an unprecedented concentration of energy in an infinitesimal point. For centuries of physics, energy and gravity were separate worlds. Energy was about light and motion. Gravity was about mass. But in 1905, Albert Einstein showed that this separation was an illusion. He demonstrated that mass and energy are not separate at all. They are two aspects of the same thing. And with that quiet realization, he set the stage for the gentle, but absolute, conclusion of our experiment. The quiet collapse. E equals mc squared. It is perhaps the most famous equation in science. Its deeper meaning is a quiet statement about the unity of the universe. E is energy, m is mass, and c squared is simply a very large number that acts as a conversion factor. What Einstein stated is that mass is a form of energy, and energy has an equivalent mass. They are interchangeable. A photon of light may be massless, in that it has no mass when at rest, but a moving photon certainly has energy. And because it has energy, it has a mass equivalent. This means that a concentration of pure energy exerts a gravitational pull. It is a tiny pull, so small we never notice it. Even the most powerful laser beams bend spacetime by an amount that is practically unmeasurable. For almost all of physics, you can safely ignore the gravity of light. But our ultimate microscope is not dealing with ordinary energies. We have gathered the Planck energy and are focusing it onto a region of space 1 Planck length across. According to E equals mc squared, this colossal concentration of energy is now indistinguishable from a concentration of mass. We have created a gravitational field. And not just any gravitational field. We have created the strongest gravitational field that is theoretically possible. This is where the second part of Einstein's legacy, his theory of general relativity, enters the story. General relativity describes gravity as the curvature of spacetime. Any concentration of mass or energy tells spacetime how to curve. Imagine a bowling ball on a stretched rubber sheet. It creates a dimple. A marble rolling nearby will have its path deflected by that curve, appearing to be pulled toward the bowling ball. The more mass you pack into a smaller space, the deeper that dimple becomes. A small star creates a gentle curve. A dense neutron star creates a much steeper one. What happens if you continue to pack more and more mass energy into a smaller and smaller volume? Eventually, you reach a point of no return. A critical density where the dimple in spacetime becomes a bottomless pit. A point where the curvature is so extreme that the escape velocity from its surface exceeds the speed of light. Nothing, not even light, can escape its pull. You have created a black hole. The boundary of this region is the event horizon, and its size is known as the Schwarzschild radius. Every object has one. For the Earth, it is about the size of a marble. To turn our planet into a black hole, you would have to crush it down to that size. Let's return to our experiment. We have the Planck energy, which has an equivalent mass known as the Planck mass, about 21 micrograms, roughly the mass of a flea's egg. Now we ask the final, critical question. What is the Schwarzschild radius for an object with the Planck mass? When you do the calculation, you arrive at a quiet, breathtaking answer. The Schwarzschild radius is the Planck length. The very act of trying to see a region of space the size of the Planck length creates an event horizon of that exact same size. The moment our energetic photon probe is focused onto that point, the energy density becomes so high that spacetime quietly collapses. An event horizon springs into existence, precisely at the location we were trying to observe. The experiment is over before it could begin. Our photon probe, the tool we were using to see, is the agent of its own confinement. It does not bounce off of anything. It does not report back what it saw. It simply creates the conditions for its own eternal imprisonment. The black hole, born from pure energy, a theoretical object known as a Kugelblitz, swallows the target, the probe, and the very information we hoped to gain. And here is the final, gentle twist. What if we were to try again, with even more energy? According to general relativity, if you add more energy to a black hole, its event horizon grows. So if you try to probe a Planck length region with more than the Planck energy, you do not get a clearer look. You simply create a bigger black hole. It is the universe's ultimate checkmate. The act of observation, when pushed to its absolute limit, becomes an act of concealment. We have not hit a technological barrier. We have hit a fundamental law of nature. The edge of measurement. The quiet failure of our thought experiment leaves us with a profound realization. The universe appears to have a fundamental limit to observation. There seems to be a smallest meaningful length that we can probe. This is the true meaning of the Planck length. It is not necessarily a pixel of spacetime. Instead, it represents the smallest distance that can be operationally measured, even in principle. This idea has been explored for decades. Physicists in the 1960s began to formally show that combining quantum mechanics and general relativity in this way implied a fundamental limit to measurement. The argument is robust. It can be reached from different starting points. We arrived at it by considering the formation of a black hole. But other lines of reasoning led to the same conclusion, through what is called the generalized uncertainty principle. The standard uncertainty principle implies that as you use more energy, your ability to pinpoint a location gets better and better. The generalized version adds a subtle correction related to gravity. It suggests that as you approach the Planck energy, the uncertainty in position stops shrinking. It hits a minimum value, the Planck length, and then, if you add even more energy, it starts to asterisk increase. Pushing harder doesn't just stop helping, it starts making things worse. It is like trying to get a clearer picture by turning up a brightness dial, only to find that after a certain point, the screen just whites out into a meaningless glare. Both lines of reasoning point to the same boundary. The Planck length is not a wall we can hope to break through. It is a boundary built from the constants of nature themselves. G, the gravitational constant. C, the speed of light, and h bar, the reduced Planck constant, which sets the scale of quantum effects. These are not arbitrary numbers. They are part of the operating system of the cosmos. To change the Planck length, you would have to change the nature of reality. So what exists below this boundary? What is happening at distances smaller than the Planck length? The honest answer is that we do not know. And we may never be able to see in the way we are used to. The universe has, in effect, a built-in privacy setting. The ultimate secrets of the infinitesimally small are guarded by black holes. This forces physics into a new and quiet territory. If we cannot look to see what is happening, how can we hope to understand it? It means our traditional method of discovery, smashing things together with more and more energy, may be destined to fail at this final frontier. The future of fundamental physics may rely on more indirect and ingenious ways to probe reality. We might look for subtle clues in the afterglow of the Big Bang, or in faint ripples in spacetime. The Planck scale is where our two great theories, general relativity and the standard model of particle physics, are no longer expected to apply. Both are thought to be approximations of a deeper theory of quantum gravity. The failure of our ultimate microscope is the clearest signpost we have, telling us precisely where our current physics breaks down. The boundary is not just an obstacle, it is a map. Beyond the veil. So, where does this leave us? We began a quest to see the smallest thing, only to find that our journey ends by creating an object of inescapable gravity. It seems like a paradox. But inside this paradox is a quiet and beautiful insight. The existence of the Planck length suggests that the smooth, continuous picture of spacetime we are used to might just be an approximation of a much stranger reality. Many physicists believe that if we could somehow peek beneath this veil, we would see a roiling, bubbling chaos. This idea, called spacetime foam, was envisioned by the physicist John Wheeler. He imagined that at this fundamental level, spacetime is not placid. It's a frenetic soup of quantum fluctuations, where tiny, virtual, black holes might be constantly popping into and out of existence. In this view, the universe we experience is like the calm surface of a deep ocean. It seems smooth and predictable, but far below, there is a turbulent world. Is there any way to test this? Scientists have tried. Some models of spacetime foam predict that high-energy light should travel a tiny bit slower than low-energy light over cosmic distances. Astronomers have looked at light from distant gamma-ray bursts, searching for this tiny delay. So far, they have found nothing. The photons arrive with remarkable synchronicity. This suggests that if spacetime is a foam, its texture is much finer than simple models predicted. But the search continues. What our thought experiment truly reveals is the boundary where our language about the universe begins to fail. Concepts like distance, before, and after may lose their meaning at the Planck scale. Asking, what is smaller than the Planck length, might be like asking, what is north of the North Pole? The very concept of space may break down. And so, our quest for the smallest ends not with an answer, but with a deeper question. It has led us from the simple act of seeing to the very edge of reality, where our most fundamental rules collide. It tells us that the universe is not just a passive stage, it is an active participant that sets its own rules, guarding its deepest secrets with an unbreakable lock. If this quiet exploration into the fabric of reality helped you see the universe in a new way, consider liking the video and subscribing to the channel. The cosmos is filled with these quiet paradoxes, and each one is a path to a deeper kind of understanding. The story of the Planck length is a humbling one. It reminds us that there are limits woven into the fabric of spacetime. The ultimate microscope, a machine born of pure curiosity, becomes the ultimate creator of ignorance, a machine that builds a wall of blackness around the very thing it sought to illuminate. It teaches us that some questions cannot be answered by looking. The smallest secrets of the universe are guarded by the most powerful objects within it. And perhaps that is the most profound lesson of all. The universe does not just contain mysteries. In some ways, the universe is the mystery. And our place is to stand in awe of its scale, its complexity, and its beautiful, unbreakable laws. The theory that unlocks the entire universe. Is there a single thought, a quiet, simple idea, that explains everything? From the first moments of the Big Bang, when our entire universe was smaller than an atom, to the impossible center of a black hole. For more than 100 years, this has been the quiet dream of physics. A theory of everything. It was a search that occupied the last decades of Albert Einstein's life, and it has since been passed down to a new generation of scientists. The hope is to write the final chapter, to find one equation, maybe no more than an inch long, that could describe all the forces that build our world. This is a journey into that search. We will travel to the very edge of what we know, to a place where our two best descriptions of the universe seem to break. And we will listen to two beautiful, but unproven, ideas that might hold the key. They are both strange. They both stretch the limits of what we can imagine. And one of them might just be right. It all begins with a quiet conflict, a deep disagreement at the heart of modern physics. For the last century, our picture of the universe has been built on two great theories. Both have been tested again and again, and have passed every test with a precision that is almost beyond imagining. They are, without question, the most successful ideas science has ever produced. But there is a problem. They contradict each other. In the most extreme places in the cosmos, they give answers that don't just disagree, they fall silent. They suggest the universe shouldn't be possible at all. This is the story of that impossibility and the long, patient search for a deeper truth that might resolve it. The Great Divide, two pillars of physics. To understand the conflict, we first have to appreciate the quiet triumphs. Our first pillar is a theory you know, one whose name has become another word for genius. Albert Einstein's general theory of relativity. When he published it in 1915, it completely changed our understanding of gravity. For centuries, we had Isaac Newton's picture. Gravity was a mysterious force, an invisible string pulling things together. It worked for predicting the orbits of planets, but it was only a description. It never explained why it was there. Einstein offered a different way of seeing. Gravity, he suggested, is not a force at all. It is a feature of the world itself. He imagined that space and time were not a fixed, empty stage. Instead, they were woven together into a single, dynamic fabric, spacetime. And this fabric wasn't flat. It could be bent and curved by the presence of matter and energy. Think of a heavy ball resting on a stretched sheet. The ball creates a dip, a curve in the fabric. A smaller marble rolled nearby will no longer travel in a straight line. Its path will bend, following the curve. It will look as if it's being pulled toward the ball. That, Einstein said, is gravity. The Earth is not pulling you down with a force. It is bending the spacetime around you, and your body is simply following the straightest possible path through that curve. It is a breathtakingly simple idea. And its predictions have proven true, time and again. We see the light from distant stars bending as it passes by massive galaxies, just as the equations predict. We've measured the subtle wobble in Mercury's orbit, a tiny detail Newton's theory couldn't explain, but which general relativity accounts for perfectly. Most wonderfully, we have directly detected gravitational waves, faint ripples in the fabric of spacetime, sent out by the collision of black holes a billion years ago. General relativity is the story of the very large, of planets, stars, galaxies, and the slow expansion of the universe itself. Our second pillar tells a story of a very different place, the strange, quiet world of the very small. This is the world of quantum mechanics. Developed in the early 20th century, it describes the rules for atoms and the particles they are made of. And those rules are deeply strange. In the quantum world, the comfortable certainty of our everyday lives dissolves. A particle, like an electron, doesn't have one definite spot until you look for it. It exists as a cloud of possibilities, a superposition of all the places it could be. Energy is not a smooth, continuous flow. It comes in discrete packets, or quanta. An electron in an atom can't have just any amount of energy. It has to occupy specific energy levels, and it can jump between them without ever existing in the space between. A quantum leap. It is a world built on chance, uncertainty, and a fundamental graininess that feels alien to us. And yet, for all its strangeness, quantum mechanics is unbelievably successful. The quiet hum of the modern world runs on this theory. The transistor, the laser, the computer chip. All of these exist because we learned to speak the quantum language. The standard model of particle physics, our quantum story of all known particles and forces, except for gravity, is the most precisely tested theory in all of science. So we have two stories. General relativity, the theory of the immense and cosmic, a smooth, geometric story of gravity. And quantum mechanics, the theory of the minuscule and subatomic, a story of probability and discrete steps. Both work perfectly in their own realms. But what happens when those realms overlap? What happens when you need to describe something that is both incredibly massive and incredibly small? This is where the conflict begins. There are two places in our universe where this happens. In the first moments of the Big Bang, when everything we can see was squeezed into a space smaller than an atom. And at the heart of a black hole, where a star has collapsed down to a point of infinite density. Physicists call these singularities. When we try to use the equations of both general relativity and quantum mechanics to describe these places, the mathematics breaks. The equations return impossible answers: infinities, an infinite density, an infinite temperature, an infinite curve in spacetime. An infinity in a physical theory is not a description of reality. It's a quiet warning. It's the theory admitting, I don't know what happens here. My story ends. The smooth, continuous fabric of spacetime from general relativity cannot handle the grainy, probabilistic nature of the quantum world. And the language of quantum mechanics, which describes forces as particles being exchanged, has no words for a force that is the shape of spacetime itself. The two theories are written in different languages, with no translator between them. This is the great, quiet disagreement in modern physics. It tells us that our understanding is not yet complete. There must be a deeper story, a more fundamental theory that can bring these two pillars together. A theory of quantum gravity. A theory that works everywhere and in all times. A theory of everything. The quest for the final story. The search for a unified theory is not new. In many ways, it's what science has always done. The drive to find a simple, underlying truth that explains the complex world we see. Newton did it when he realized the same force that makes an apple fall also holds the moon in its orbit. Maxwell did it when he showed that electricity, magnetism, and light were all just different aspects of the same thing. But the final unification, the one that would include gravity, became the quiet obsession of Albert Einstein. After finishing general relativity, he spent the last 30 years of his life in a long, patient search for what he called a unified field theory. He dreamed of a single story that could unite his theory of gravity with electromagnetism. He did not find it. Looking back, his search was happening too soon. The other two fundamental forces, the strong and weak nuclear forces, were not yet understood. More importantly, he was deeply uncomfortable with the strange, probabilistic world of quantum mechanics, famously saying that God does not play dice. He was trying to write a unified story using only the old language of classical physics, while a new quantum language was being discovered all around him. But the dream did not end with him. As our understanding grew, the problem only became clearer. The standard model of particle physics successfully united the other three forces in the quantum language, leaving gravity as the lone outlier. The need for a quantum theory of gravity became the most important and difficult question in physics. Why is it so hard? The main reason is a lack of evidence. The world where quantum gravity matters is a world of unimaginable energies and impossibly small distances, the so-called Planck scale. To see this world directly, we would need a particle accelerator the size of our galaxy. So, for now, physicists are left to navigate by the light of mathematics and a sense of beauty alone. This has led to two main paths forward, born from two different philosophies. They represent two different bets on how the universe is ultimately built. One path suggests our current story is not big enough. It imagines new ingredients, new symmetries, even new dimensions of space, trying to build a grand structure from which our universe will emerge. This is the path of string theory. The other path is more careful. It tries to build a quantum theory of gravity using only the ingredients we already have: general relativity and quantum mechanics. It doesn't add new dimensions or new particles. Instead, it asks us to look at space and time in a completely new way. This is the path of loop quantum gravity. These are our two beautiful, unproven ideas. Two possible keys to unlocking the universe. For decades, they have been developed quietly, by different groups of physicists, each believing their path holds the most promise. And they could not be more different. Contender 1: the cosmic symphony of string theory. Our first contender, string theory, began its life in the 1960s. It started not as a theory of everything, but as an attempt to describe one of the nuclear forces. It was soon replaced in that role, But a few physicists noticed something remarkable in the mathematics. The theory held a quiet, unexpected piece of a puzzle. Something that looked like a quantum description of gravity. The central idea of string theory is simple and very deep. It asks us to let go of a belief we've held our whole lives. That the smallest bits of matter are tiny, solid points. We've always imagined that if you could zoom in on an electron, you would just see a smaller and smaller dot. String theory says this is wrong. If you could zoom in to an impossibly small scale, you would find that an electron is not a point. It is a tiny, one-dimensional, vibrating loop of energy. A string. In this view, everything in the universe, every particle of matter, every carrier of force, is made of these same fundamental strings. So what makes an electron different from a quark? The answer, the theory says, is music. Just as a violin string can vibrate at different frequencies to produce different notes, these fundamental strings can vibrate in different patterns. One vibrational pattern, one note, appears to us as an electron. A different pattern appears as a photon. Another, a quark. The universe, in this view, is a grand cosmic symphony. The rich, diverse world of particles we see is just the harmony created by the vibrations of these tiny strings. This is the theory's quiet, unifying power. Instead of a confusing collection of different particles, there is just one thing: the string. This elegant picture also does something that had proven impossible before. Among the string's possible vibrations, one particular note always appears in the mathematics. This vibration has the exact properties of the graviton, the hypothetical quantum particle of gravity. For the first time, gravity wasn't being forced into a quantum story. It simply appeared, an expected note in the symphony. This suggested that string theory wasn't just a theory of quantum gravity. It might be the theory. But this beautiful idea comes with a surprising requirement. The mathematics of string theory doesn't work in the universe we know, with 3 dimensions of space and 1 of time. The equations only hold together if the universe has extra spatial dimensions. Specifically, the theory requires 9 dimensions of space and 1 of time. So where are they? The theory's answer is that these extra dimensions are curled up, or compactified, on a scale so small we could never notice them. The classic analogy is a garden hose. From far away, it looks like a one-dimensional line. But as you get closer, you realize it has a second dimension, a tiny circle you can move around. String theorists suggest that at every point in our 3-dimensional space, there exists a tiny, intricate, 6-dimensional shape. These shapes are so small that the strings making up our world are too large to ever feel them. We are like giants walking on a tightrope, completely unaware of its thickness. The exact shape of these hidden dimensions is very important. The way they are curled and twisted determines the notes the strings can play. And since the notes determine the particles and forces, the shape of these extra dimensions dictates the laws of physics. This leads to one of the theory's most beautiful features, and one of its deepest problems. It turns out there isn't just one way to curl up these extra dimensions. There are a staggering number of possibilities. The current estimate is somewhere around 10 to the power of 500. Each of these possibilities would create a universe with its own unique set of physical laws. This vast collection of possible universes is known as the string theory landscape. Our universe would be just one valley in this immense landscape of possibilities. On one hand, this could explain why the laws of nature in our universe seem so perfectly tuned for life. We simply live in one of the rare universes where the laws allow for it. On the other hand, it's a source of deep frustration. If a theory can describe almost any universe, how can it tell us anything specific about our own? Critics suggest that a theory that explains everything, in the end, explains nothing. Some wonder if it has become a kind of beautiful mathematics, separate from the physical world. String theory remains a work in progress. It is a vast, intricate story that is still being written, one that has given us deep new ways of thinking about our world. It offers an elegant vision of a universe unified by the music of vibrating strains. But the quiet questions remain. Do the extra dimensions exist? And is this beautiful music the true sound of reality, or just a seductive echo? We are diving deep into the biggest questions in science, exploring the very nature of reality itself. If this quiet exploration into the fabric of the cosmos is sparking your curiosity, and you want to continue exploring the frontiers of physics, consider taking a moment to subscribe to the channel. It allows us to keep making these deep dives into the wonderful, strange, and mind-bending universe we find ourselves in. Your support truly makes it all possible. Now, let's turn to our other contender, an idea that takes a completely different approach to building reality. Contender 2: the quantum fabric of loop quantum gravity. If string theory is a story of addition, our second contender, loop quantum gravity, is a story of careful listening. It begins with a different philosophy. It doesn't imagine extra dimensions or new particles. Its goal is more focused: to take Einstein's general relativity and quantum mechanics, the two stories we know are true, and find a way to make them speak to each other. Loop quantum gravity, or LQG, comes from the idea that gravity is, first and foremost, a theory of geometry. It takes Einstein's central idea, that gravity is the shape of spacetime, and asks a simple question: if the matter and energy that shape spacetime are quantum, shouldn't spacetime itself be quantum, too? LQG's answer is yes. And this leads to its core, revolutionary idea: space is not a smooth, continuous background. If you could zoom into the Planck scale, you would find that space itself is granular. It is made of discrete, indivisible chunks. Imagine a t-shirt. From a distance, it looks like a smooth, two-dimensional surface. But as you look closer, you see the individual threads, woven together in a network of loops and knots. LQG proposes that the fabric of spacetime is like this. It is a network of interconnected, finite loops, woven into something called a spin network. This is not an analogy. LQG predicts that there is a literal, physical smallest possible area and a smallest possible volume. Just as you can't have less than one quantum of light, a photon, you cannot have a piece of space smaller than a certain fundamental size. These are the atoms of space, the pixels from which reality is built. Time, too, doesn't flow like a smooth river. It ticks by in discrete, quantized steps. In this picture, space-time is no longer a passive stage. The spin network itself is space. Gravity is not a force that moves through space, it is a property of the network itself. This idea is called background independence, and it's one of LQG's proudest features, something many feel is more true to Einstein's original vision. This atomic structure of spacetime has profound implications. Its greatest triumph is in resolving the very problem that started our search, the singularity. In general relativity, a black hole singularity is a point of zero volume and infinite density. In LQG, this can never happen. There is a smallest possible volume. You simply cannot crush matter into an infinitely small point. As matter collapses, the density increases to unimaginable levels. But when it reaches a certain threshold, the quantum geometry of spacetime itself pushes back, creating a powerful repulsive force that prevents a singularity from forming. This leads to one of the most spectacular predictions of loop quantum gravity, the Big Bounce. According to LQG, the Big Bang may not have been the beginning of time. Instead, our universe might have arisen from the collapse of a previous universe. As that universe collapsed, its density reached the limit, the quantum pressure kicked in, and it bounced, re-exploding outwards to become the expanding universe we see today. The Big Bang is replaced by a big bounce. The singularity vanishes, replaced by a quiet bridge from one universe to the next. But, like string theory, LQG has its own significant challenges. While the theory gives a beautiful description of the quantum world, it has been very difficult to show how this pixelated geometry smoothly becomes the continuous spacetime we experience. How does the woven t-shirt look so smooth from far away? Answering that is a major, unsolved problem. And, like string theory, it suffers from a lack of experimental evidence. The granularity of space it predicts is far too small for us to see directly. There were hopes that high-energy light from distant cosmic events might be slightly slowed by spacetime's pixels, but so far, observations have shown no evidence of such an effect. Loop quantum gravity presents us with a radically new vision of reality, a world woven from quantum threads. It is a more conservative and arguably more direct approach. But whether its granular picture of spacetime is the correct one remains an open and deeply compelling question. Two visions, one universe. So we are left with two different stories, two beautiful and profoundly different ideas about our universe. On one side, we have string theory, the grand unifier. A story of breathtaking ambition, where all of reality emerges as the music of vibrating strings. Its mathematical elegance is seductive. Gravity is not added on, it is an inevitable note in the symphony. But its beauty requires a universe of hidden dimensions we cannot see, and it presents us with a bewildering landscape of possible universes, making it difficult to test. On the other side, we have loop quantum gravity, the focused listener. It doesn't dream of extra dimensions. It takes on the hardest problem directly: quantizing gravity. Its vision is a universe where spacetime itself is a quantum fabric woven from discrete loops. This pixelated reality elegantly dissolves the problem of infinities, replacing the Big Bang with a big bounce. But it struggles to show how our smooth world emerges from its quantum threads, and it has yet to fully include the other forces of nature. The debate between them touches on the soul of physics. Does the universe prefer the sprawling, all-encompassing beauty of string theory? Or the quiet, careful logic of loop quantum gravity? The ultimate decider in science is always evidence. And here, in this search, the world has so far been quiet. We cannot see the strings vibrate, nor can we resolve the individual atoms of spacetime. Without that feedback, how can we know if we are on the right path? But physicists are not giving up. They are searching for quiet, indirect clues. Could a faint signature of the Big Bounce be hidden in the afterglow of our universe's birth? Could there be hints in the behavior of black holes? There are even whispers of a thaw in the Cold War between the two theories. A new generation of physicists is beginning to explore the connections between them. Perhaps they are not entirely different. Perhaps, in some way we don't yet understand, string theory and loop quantum gravity are two different ways of telling the same story. The quest for a theory of everything is a story of human ambition at its most extreme. It is a testament to our relentless desire to understand, to find order in the world, and to read the logic of the cosmos. We are searching for the source code of reality. And while we haven't found it yet, the search itself has revealed a universe far stranger, and far more beautiful, than we ever could have imagined. We began with a quiet conflict, the impossible disagreement between our two greatest theories of the universe. We've journeyed through two possible resolutions: the cosmic symphony of vibrating strings in hidden dimensions, and the quantum fabric of a granular, bouncing spacetime. Both theories are breathtaking, both resolve the paradox of infinity, and both remain just beyond the reach of proof. So, have we found the theory that unlocks the entire universe? The honest answer is no. Not yet. The quest continues. The final theory could be one of these, a mixture of the two, or something so new that we haven't even begun to dream of it yet. But the lack of a final answer isn't a failure. It is the nature of a question this large. We are finite beings, living for a brief moment on a tiny planet, trying to comprehend the totality of existence. The fact that we can even ask these questions, that we can write down equations that describe the birth of the universe and the heart of a black hole, is a quiet miracle. The journey for a theory of everything is the ultimate expression of human curiosity. It's a story written in the language of mathematics, fueled by a desire to know our place in the cosmos. We don't know how the story will end, but we do know that the next chapter is being written right now, in the minds of a dedicated few, who dare to ask the biggest question of all. Why is the universe the way it is? And what, in the end, is it made of? The physics wall we can never break through. For centuries, we have looked out at the universe and tried to understand it. We've charted the stars, split the atom, and peered back to the dawn of time. But what if there's a limit? A point in our knowledge that we can't seem to move past? This isn't a wall made of stone or metal. It's a wall in our understanding, and it stands between our two best descriptions of reality: the grand, sweeping dance of gravity, and the strange, jittery world of quantum particles. This is the story of that wall, why our most powerful machines have failed to break it, and how a new kind of science, quiet and clever, might finally be showing us a way to see what's on the other side. In the first moments of the universe, all the forces of nature were one. Gravity, electromagnetism, the forces that hold atoms together, they were all part of a single, unified whole. As the universe cooled, they separated, each with its own set of rules. We've learned to connect most of them back together, but gravity remains apart. The search to reunite it with the others, to find a theory of quantum gravity, is perhaps the greatest goal in modern physics. But the universe has hidden the clues we need. It's hidden them behind an energy barrier so immense, it has a name: the Planck scale. The Planck scale isn't a location you can travel to. It's a threshold of energy and smallness where our ideas of space and time begin to break down. Below a certain, incredibly small scale, about 10 to the minus 35 meters, space is no longer smooth. It becomes a chaotic, foaming sea of quantum energy. To see this, to observe gravity behaving as a quantum force, we would need to focus an incredible amount of energy into one point. The amount of energy required is called the Planck energy, about 10 to the 19 billion electron volts. To put that number into perspective, our most powerful machine, the Large Hadron Collider, smashes particles together with tremendous force at around 14 trillion electron volts. But the Planck energy is a quadrillion times greater. The gap between what our best machine can do, and what we need to do, is larger than the gap between the size of a single atom and the entire planet Jupiter. It is a barrier built by the laws of nature itself. We know where the secrets are. We just haven't been able to build a tool big enough to reach them. So we tried to build those tools. We built monuments to our own curiosity: particle accelerators. The Large Hadron Collider is the greatest of them. A 27-kilometer ring where we accelerate particles to nearly the speed of light, guided by magnets colder than deep space. When they collide, for a fraction of a second, we recreate the conditions of the early universe. It was here that we found the Higgs boson, the final piece of our current model of particle physics. A monumental achievement, but we had hoped to see more. We thought we might see tiny black holes appear and vanish, or clues that gravity was leaking into other dimensions, or that the very fabric of spacetime wasn't perfectly smooth. We found none of it. Only silence. Our most powerful tool had slammed against the wall, and couldn't even leave a mark. The problem became clear. To reach higher energies, we need even bigger machines. A future collider could require a tunnel nearly 100 kilometers long, circling an entire city. And even this giant would fall hopelessly, comically short of the Planck energy. This is because particles like electrons radiate their energy away when forced into a circle, and even protons, which are more stable, are messy bags of smaller particles, diluting the impact. The direct approach, the method of simply smashing things together harder, had brought us to a dead end. The universe was not giving up its secrets easily. But sometimes in science, when a path is blocked, the solution is not to push harder, but to find a different path altogether. A new idea has been growing. It trades immense power for incredible precision. Far from the giant tunnels and billion-dollar budgets, a quiet revolution is happening in small laboratories. Scientists are realizing you may not need to recreate the Big Bang to see quantum gravity. You just need to design an experiment that is clever enough. The central idea is built on one of quantum mechanics' strangest features: entanglement. Entanglement is a connection between two particles. They behave as a single system, even when separated. If you measure one, you instantly know the state of the other. Einstein called it spooky action at a distance. The new question is this: can gravity, and only gravity, create this link? If it can, that would be the first real evidence that gravity is a quantum force. Proving it doesn't require enormous energy. It requires creating a system so perfectly isolated that the only thing connecting two tiny objects is their own gravitational pull. It is a challenge of precision, not power. These new experiments are happening now. Here is how they work. Imagine two microscopic objects, perhaps tiny crystals of diamond. The first step is to put each one into a quantum superposition. This means each object exists in two places at the same time. You then have two of these quantum objects, held a tiny distance apart. Their own gravity will pull on each other. But because they are each in two places at once, that gravitational pull becomes a complex interaction. If gravity is quantum, this interaction will entangle them. Their fates will become linked. After a short time, you check them. If you find they are entangled, you have witnessed gravity behaving in a quantum way. You have seen a glimpse of what's beyond the wall. The challenges are enormous. Gravity is incredibly weak. Any stray vibration, any change in temperature, or even the pull from a passing cloud could ruin the experiment. But scientists are finding clever ways to work around these problems. Some use tiny diamonds with specific flaws inside them, which act like handles that can be controlled with lasers. Others levitate tiny spheres in a vacuum, cooling them with lasers until they are almost perfectly still, in their lowest possible energy state. These experiments are not just looking for a simple yes or no. They are designed to measure the asterisk strength of the connection, which could tell us not just if gravity is quantum, but something about how it is quantum. We are entering a new era of this search, one defined not by force, but by finesse. For a century, our understanding of the universe has been split in two. General relativity describes the world of the very large, planets, stars, and galaxies. Quantum mechanics describes the world of the very small. Both work perfectly in their own realms. But between them stands the Planck wall, a place where both theories fail, and our understanding stops. We tried to break through that wall with force. We built the largest machines in human history. But the wall did not move. Now, science is taking a new path. The quiet revolution of tabletop experiments has opened a new front in this search. We are trading the sledgehammer for the scalpel, immense energy for exquisite precision. We do not know what we will find. Will we see the signature of entanglement that proves gravity is quantum? Or will the universe show us something even stranger? What is certain is that we are no longer just staring at a blank wall. We are listening for echoes, looking for cracks. The great search for a final theory is not over. It may have just begun. If you found this journey to the edge of reality as fascinating as we did, consider subscribing and sharing this video. And let us know in the comments, what secret do you think lies behind the Planck wall? The discovery that will force humanity to question reality. For more than a century, our understanding of the universe has rested on two colossal pillars. They are the two most successful theories ever conceived by the human mind. Each describes a facet of reality with breathtaking precision, and they are utterly, fundamentally, incompatible. This is not the story of a new gadget or a faster computer. It is a quiet exploration into a contradiction so deep it has forced us to question the nature of space, the flow of time, and the very ground of our existence. The effort to resolve this contradiction is the quest for a theory of quantum gravity. At the heart of this quest lies a revelation that goes far beyond complex mathematics. It is a journey into a puzzle that began at the very first moment of time, a puzzle that compels us to confront the true, strange nature of the cosmos and our place within it. The two realities. To understand the problem, we must visit the two realms that physics describes. For the last century, this division has served us well. But it is a separation that cannot last. The first pillar is Albert Einstein's general theory of relativity. It is a theory of the grand, cosmic scale. Imagine spacetime as a vast, pliant fabric, four-dimensional and unseen. General relativity tells us that massive objects, like stars and planets, create gentle dips and curves in this fabric. What we experience as gravity is simply the feeling of moving along the straightest possible path through this curved geometry. It is an idea of remarkable elegance, and it works flawlessly. The GPS that guides us relies on its corrections. We have seen light from distant galaxies bend around massive objects, just as Einstein predicted. We have detected the faint ripples in spacetime itself, gravitational waves, from the collision of black holes a billion light-years away. On the scale of galaxies and the graceful dance of planets, general relativity is sovereign. It describes a universe that is smooth, continuous, and predictable. But then, we have the second pillar, quantum mechanics. If general relativity is a stately, flowing river, quantum mechanics is a flickering, uncertain haze. It governs the world of the incredibly small, the realm of atoms, electrons, and photons. Here, all the familiar rules dissolve. Particles do not have definite locations until they are measured. Instead, they exist in a cloud of probabilities, a state known as superposition. Two particles can become entangled across vast distances, so that observing one instantly influences the other, a phenomenon Einstein called spooky action at a distance. Energy is not a smooth continuum, but comes in discrete, indivisible packets called quanta. The quantum world is not smooth, it is granular. It is not deterministic, it is probabilistic. It is, by all accounts, deeply strange. Yet, like relativity, it is staggeringly successful. The device on which you are watching this, modern medicine, and nearly all of our technology is built on a mastery of this quantum realm. For decades, this division worked. Physicists used relativity for the large and quantum mechanics for the small. It was a practical arrangement, an agreement to use the right tool for the right scale. But there are two places in the universe where this separation no longer holds. Two places where the unstoppable rules of the quantum world meet the immovable grandeur of general relativity. These are the heart of a black hole and the moment of the Big Bang. Inside a black hole, an immense mass is crushed into a region of unimaginable density. Here, gravity is overwhelmingly strong, requiring general relativity, but the space it occupies is subatomic, the domain of quantum mechanics. At the Big Bang, the entire observable universe was smaller than an atom, an environment where both theories must have applied. And when physicists try to use the equations of both theories in these extreme places, the mathematics begins to fail. The equations do not just become difficult, they yield nonsensical results, like infinities, a clear sign that our understanding is incomplete. The smooth, elegant curves of spacetime simply cannot coexist with the jittery, quantized chaos of the subatomic world. This conflict is known as the problem of quantum gravity. It is the single greatest missing piece in our map of reality. Two paths to a deeper truth. So, how does one resolve a contradiction of such cosmic proportions? For decades, the search for a theory of quantum gravity has followed two principal paths, two different schools of thought for cracking the case. The first is the more famous of the two, String theory. It looks at the conflict between the large and the small and proposes a radical, yet elegant, solution. It suggests that if we could zoom in on the fundamental particles we know, electrons, quarks, photons, we would not find dimensionless points. We would find something else. Minuscule, one-dimensional, vibrating filaments of energy. Tiny, oscillating, strains. In this view, every particle is simply a different note played on one of these fundamental strains. An electron is a string vibrating in one pattern, a photon in another. The entire rich and diverse collection of particles is just the symphony of these vibrating strains. What is truly remarkable is that within this framework, one particular vibration naturally appears with the exact properties of the graviton, the hypothetical particle that carries the force of gravity. In string theory, gravity is not an awkward addition, it is an inevitable part of the music. But this approach presents its own profound challenges. For the mathematics to cohere, string theory requires that the universe has more dimensions than the 4 we experience, perhaps 10 or 11 in total. These extra spatial dimensions are thought to be curled up into tiny, intricate shapes, far too small for us to perceive. Furthermore, the theory's equations do not point to just one possible universe, but to a vast landscape of possibilities, perhaps 10 to the power of 500, each with its own physical laws. With so many potential universes, it becomes difficult to find our own, or to make testable predictions. This has led some to wonder if string theory is as much a branch of mathematics as it is of physics. This brings us to the second path, loop quantum gravity or LQG. This approach is less ambitious, focusing only on the problem of quantizing gravity itself, rather than unifying all the forces of nature. LQG takes a more direct route. It begins with Einstein's theory of general relativity and attempts to apply the rules of quantum mechanics to the fabric of spacetime itself. It asks a simple, powerful question. What if spacetime is not a smooth, continuous sheet, but is instead made of fundamental, indivisible units? In the world of loop quantum gravity, if you could zoom down to the smallest possible scale, the Planck scale, a level so small that if an atom were the size of the known universe, the Planck scale would be the size of a single tree, you would find that space is not continuous. You would find a network of interwoven, finite loops. These loops are the fundamental atoms of space. They do not exist in space. Their connections to one another create space. Area and volume themselves are quantized. There is a minimum possible size for a patch of area or a chunk of volume. Space, in this picture, is like a piece of fabric. From a distance, it appears smooth. But up close, you see it is made of individual threads woven together. Time is the process of this network of loops rearranging itself, one frame to the next. This granular structure of spacetime elegantly resolves the problem of infinities that appears when gravity and quantum mechanics meet. A black hole singularity, for instance, is no longer an infinitely dense point, but a region of incredibly dense, yet finite, quantum geometry. This approach is compelling because it does not require extra dimensions or undiscovered particles. However, it faces its own difficult questions. One of its greatest challenges is demonstrating how the smooth, continuous spacetime of Einstein's relativity emerges from this pixelated, quantum-level description. And yet, for all their differences, both of these brilliant, but unproven, theories began to point toward a shared conclusion, a deeply unsettling possibility. They both suggested that the very stage on which our universe performs, the fabric of spacetime itself, is not fundamental. The disappearance of space. This is the moment the search changes. It is no longer just about finding a new equation. It is about confronting a truth that challenges our most basic perception of the world. Both string theory and loop quantum gravity, in their own ways, are whispering the same thing. Spacetime is emergent. What does it mean for something to be emergent? It means it is not a primary ingredient of reality, but a secondary effect that arises from the collective behavior of something deeper. Think of the concept of wetness. A single molecule of H2O is not wet. The question does not make sense. Wetness is a property that emerges from the interactions of countless water molecules together. The individual molecules are not wet, but their group behavior gives rise to the quality we call wetness. In the same way, a single atom does not have a temperature. Temperature measures the average motion of a large group of atoms. It is an emergent, statistical property of a system. Theories of quantum gravity are suggesting that spacetime is like wetness or temperature. The fundamental components of reality, whatever they are, do not exist in space or time. Instead, space and time are the collective, large-scale effects of the interactions of these fundamental ingredients. As one physicist starkly put it, spacetime is doomed. For loop quantum gravity, this idea is quite direct. The theory explicitly constructs space from non-spatial atoms, the loops. The concept of location is relational. A loop is defined only by what it is connected to. The fabric of the cosmos is woven from these fundamental relationships. In string theory, the idea is more subtle, but just as profound. It comes from what is known as the holographic principle. This principle suggests that all the information contained within a volume of space, this room, for example, can be described by a theory that lives only on the two-dimensional boundary of that space, on its walls. This has led some physicists to believe our three-dimensional universe might be an emergent, holographic projection of a more fundamental, lower-dimensional reality. Some have even proposed that the geometry of spacetime itself emerges from the web of quantum entanglement. In this view, the distance between 2 points in space is a reflection of how entangled they are. For our entire lives, we have thought of space as the empty container that holds everything. But these theories, our leading candidates for describing ultimate reality, tell us this is likely an illusion. The container is not fundamental. It is built from the relationships between the things it contains. This is the first quiet revelation. The solid, stable arena of reality is dissolving into a network of pure information. But if space itself is a construction, what does this imply for its partner, time? It is here that the implications touch our own experience most deeply. The stillness of time. Our experience of time is perhaps the most fundamental aspect of our consciousness. We feel it as a constant, flowing river, carrying us from a fixed past, through a fleeting present, into an open future. But according to these lines of inquiry, this deeply personal experience might be the grandest illusion of all. The problem of time, in physics, is not new. It represents a conceptual clash between how general relativity and quantum mechanics treat time. In Einstein's relativity, there is no universal now. Time is another dimension, woven together with space into the spacetime fabric. This leads to a picture known as the block universe, where the past, present, and future all exist simultaneously and are equally real. The flow of time is a subjective illusion. The entire timeline of the universe is simply there, a static, four-dimensional block. Quantum mechanics, on the other hand, traditionally treats time as something special and absolute, a universal clock against which all else evolves. When physicists attempt to combine these two ideas, something strange happens in the mathematics. In many formulations of quantum gravity, the variable for time, t, simply vanishes from the most fundamental equations. The universe, at its deepest level, appears to be timeless. It is described by a state that does not change. If there is no time at the fundamental level, where does our experience of a flowing river come from? The emerging view is that time, like space, is not fundamental, but is a secondary phenomenon. One prominent idea is that our sense of time's arrow is linked to entropy, the universe's tendency to move from order to disorder. Another, more subtle idea connects the emergence of time to quantum entanglement. It has been shown mathematically how a static, timeless quantum system, when viewed from the inside by a part of that system, can appear to evolve. Time, in this view, does not exist globally. It emerges locally from the relationships between entangled parts. The implications are quiet and staggering. There may be no universal river of time. There may be no master clock for the cosmos. There may only be a timeless, static reality described by the fundamental equations. Our experience, the feeling of moments passing, would then be a subjective illusion, created by our limited perspective as beings within this static whole. We are like a reader scanning a single line in a book that already contains the entire story, from beginning to end. The flow is in our act of reading, not in the book itself. The universe isn't happening, it just is. We are journeying to the edge of human understanding, where our most fundamental assumptions are being questioned. If this kind of calm exploration into the nature of reality is something you find valuable, consider subscribing to the channel. We are about to venture into the most speculative part of our story, where we ask the final question. If space and time are not real, what does that mean for the consciousness that perceives them? Consciousness and the structure of reality. We now arrive at the most speculative portion of our journey. The investigation into the fabric of the cosmos has led to a radical possibility that the foundational elements of our world, space and time, are emergent illusions. This revelation has fallout, and it lands directly on the last bastion of our certainty, our own conscious experience. Here, we must step carefully. We are leaving the established, though still theoretical, realm of quantum gravity and entering the territory where physics, neuroscience, and philosophy intersect. This is a place of bold questions, not firm answers. The central mystery is this: if the fundamental reality is a timeless, non-spatial web of quantum information, then where does this come from? Where does the vivid, solid, and flowing world of our subjective experience arise? This is a modern reframing of what philosophers call the hard problem of consciousness. And it is here that some researchers have dared to ask a provocative question. What if consciousness is not just a passive observer of this process, but is somehow intimately involved? This line of thinking is most famously associated with the orchestrated objective reduction, OR theory, proposed by the physicist Sir Roger Penrose and the anesthesiologist Stuart Hameroff. It is crucial to state that this theory is controversial and not accepted by the majority of scientists. However, it serves as a powerful example of the kind of paradigm-shifting questions that the puzzle of quantum gravity encourages. The theory proposes that consciousness is not simply a product of complex computation in the brain. Instead, it posits that moments of conscious experience arise from quantum processes occurring within tiny structures inside our neurons called microtubules. In this radical view, consciousness is not something the brain creates, but a feature of the universe that the brain has evolved to harness. Again, it is vital to emphasize the speculative nature of this idea. Critics point out that the brain seems far too warm and complex to sustain the delicate quantum states the theory requires. But we do not need to accept OR as fact to appreciate the profound philosophical door it opens. The theory is a symptom of a much deeper puzzle. The investigation into quantum gravity has dissolved the solid world into abstract information. It has removed the steady flow of time. It has blurred the line between the observer and the observed. In doing so, it forces us to re-evaluate the very nature of physical reality. The true revelation is not a specific theory, but the asterisk necessity of asking such questions. The discovery that will force us to question reality is the dawning realization that the neat separation between the objective world, out there, and the subjective world, in here, may not exist at the fundamental level. If spacetime is an emergent property, then the very ground beneath our feet has vanished. And we are left to ask the most fundamental question of all. What is the relationship between the quantum code of the universe and the mind that is somehow, able to read it? A world remade. Where does our exploration leave us? We began with a deep incompatibility between the two pillars of modern physics. We followed two different paths of inquiry, string theory and loop quantum gravity. And along the way, we uncovered clues that point toward a profound verdict: that our most intuitive and common-sense understanding of reality is likely wrong. The universe is not a collection of objects sitting in a pre-existing space, evolving along a universal timeline. That is a comforting, but ultimately incorrect, user interface for a much deeper and stranger operating system. The reality hinted at by our best theories is a timeless, non-spatial realm of pure information. Spacetime, the solid world, the flow of moments, all of it emerges from this deeper substrate, a holographic projection born from a web of relationships and entanglement. This realization is the discovery that will compel us to question reality. It is the understanding that the ground beneath our feet is not ground at all. The implications will ripple through every aspect of human thought. It redefines our place in the cosmos. We are not just inhabitants of the universe, we are emergent patterns within it. Our perception of a flowing reality is a local, subjective experience, born from our limited perspective inside a static whole. The true revolution will be philosophical. The discovery of quantum gravity will be the final step in a long journey of cosmic humility. We once thought we were at the center of the universe. Copernicus moved the Earth. Hubble moved our galaxy. The discovery of emergent spacetime may decenter us from reality itself. It shows us that our entire perceived world is a clever, convenient illusion. This brings us to the final, lingering question. The quest for quantum gravity has revealed a universe that looks less like a machine and more like a vast, interconnected thought. A story written in a language of information and relationships. And so, we are left to wonder: if the world is a story, are we merely its readers? Or are we, somehow, a part of its telling? What is the true nature of the consciousness that is asking this question? That is the discovery that will not just change science, but will change us forever.